Welcome, we're so happy you tuned in tonight. Before we get started, I'd love to know, where are you watching from? Drop it in the comments. Now, let's get comfortable and drift into deep, peaceful sleep together. The universe can be thought of as everything that can interact with everything else within a shared space and time. It's a gentle starting point, this idea of interaction and connection. When we say the universe, we're usually gesturing toward all space, all time, and everything contained within them, every atom, every photon of light, every distant galaxy, and every quiet moment. But the word universe is flexible enough to hold different meanings depending on context. In everyday language, it can mean the biggest possible backdrop, the widest frame we can imagine for any event or thought. It's the quiet background behind every moment of existence, steady and encompassing. The universe includes matter, which is the stuff we can touch and measure, atoms arranged into stars, planets, rocks, water, and living things. But it also includes energy, which flows and transforms, showing up as light streaming from distant suns, as heat radiating from warm surfaces, as motion carrying waves, through empty space. Matter and energy are two aspects of the same underlying reality, connected by relationships that scientists have mapped with patience and care over centuries. Beyond matter and energy, the universe contains the rules themselves, the patterns that describe how things behave. Gravity pulls objects toward each other with a strength that depends on their masses and the distance between them. Light moves at a constant speed through empty space, always travelling in straight lines unless something bends its path. These rules are woven into the fabric of existence, invisible but utterly reliable. A helpful way to think about the universe is to realize it's not only made of things, but also of the spaces between things. Space is not just emptiness waiting to be filled. It has properties of its own. It can stretch and curve. It can carry ripples, waves of gravitational influence that move outward from violent cosmic events like colliding black holes. When we talk about space, we're talking about something that participates in the universe's story, not just a passive stage where the story happens. This shift in perspective, from space as a container to space as an active participant, is one of the quiet revolutions in modern physics, and it changes how we understand distance, motion, and time itself. Time is part of the universe too, flowing steadily forward and giving events their order. We experience time as a sequence, one moment following another, cause preceding effect, memories accumulating in one direction. Time creates the possibility of change, of transformation, of histories unfolding. Without time, there would be no motion, no growth, no stories of stars forming and galaxies evolving. Time and space are linked so closely that physicists often speak of them together as space-time, a unified structure where position and duration intermingle. This union of space and time feels abstract at first, but it reflects something deep about the way the universe actually works, something we can measure and test and rely upon. Scientists study the universe using measurements, models, and careful observations. They gather data from telescopes that collect light across many wavelengths, from spacecraft that venture to distant planets, from particle accelerators that probe the smallest scales of matter. They build mathematical models to describe patterns, make predictions, and test whether those predictions match what actually happens. This process is methodical and collaborative, with thousands of people around the world contributing pieces to a vast shared puzzle. The picture that emerges is not complete. There are gaps, uncertainties, questions that remain open. But it is remarkably coherent, and it grows more detailed with each passing decade. Even with all our tools and all our understanding, the universe still has room for gentle mystery. There are questions we cannot yet answer, phenomena we have not fully explained, scales of reality we have only begun to explore. This incompleteness is not a failure. It's a reminder that curiosity is inexhaustible, that wonder is always available, that the universe invites us to keep looking, keep asking, keep discovering. For tonight, though, these mysteries need not be urgent. They can rest quietly in the background, patient and unthreatening, while we turn our attention to what we do understand, and let that understanding settle into the mind like soft light through a window. Now that the word universe feels settled, we can drift into what we can actually see and measure, like looking through calm, clear glass. The observable universe is the part of the universe we can detect, because its light has had time to reach us. This is an important distinction. The universe might be vastly larger than what we can observe, or it might even be infinite, but we are limited by a simple fact. Light travels very fast, but it still takes time to cross large distances. Since the universe has a finite age, about 13.8 billion years according to current measurements, there is a maximum distance from which light could have reached us since the beginning. Everything beyond that distance is for now unobservable, not because it doesn't exist, but because its light simply hasn't arrived yet. Looking far into space also means looking back into the past, because we see light that left its source long ago. When you observe a star 10 light years away, you're seeing it as it was 10 years ago. When you observe a galaxy a billion light years away, you're seeing it as it was a billion years ago, when the universe was younger, when the structures of matter were less evolved. This time delay effect turns telescopes into time machines of a sort, instruments that reveal the universe's history written in the arrangement and appearance of distant objects. The night sky becomes an archive, layer upon layer of ancient light, each layer carrying information about a different era. Telescopes are like patient collectors of faint light, gathered over time. Early telescopes were simple lenses or mirrors, small enough to hold in your hands, but they opened up the heavens in ways that amazed their users. Over centuries, telescopes have grown larger, more sensitive, more specialized. Some are built on remote mountaintops where the air is thin and steady. Some orbit above Earth's atmosphere, avoiding the distortions and absorptions that air can cause. Some are designed to detect specific kinds of light, radio waves, infrared, ultraviolet, X-rays, that our eyes cannot see. Each kind of light reveals different features of the universe, like different filters applied to the same scene. Some objects are too dim to see directly, but we can still detect their effects. A dark cloud of gas might block the light of stars behind it, creating a silhouette. A massive object might bend the light from something farther away, creating a distorted image. A faint galaxy might be too distant to photograph clearly, but its gravity might influence the motion of other galaxies nearby. Astronomers have become skilled at reading these indirect signs, piecing together a picture of the universe from clues that are subtle, scattered, and patient. Astronomers learn from many kinds of light, not just the kind our eyes see. Radio waves can reveal cold gas clouds and the remnants of ancient explosions. Infrared light can penetrate dust and show us warm regions where stars are forming. Visible light is the band we're most familiar with, the rainbow from red to violet. Ultraviolet light comes from hot, energetic stars and glowing gas. X-rays trace extremely hot regions, like the material swirling into black holes or the gas in galaxy clusters heated to millions of degrees. Gamma rays mark the most violent events, like supernovae and the collisions of neutron stars. By observing across this full spectrum, astronomers build a richer, more complete understanding of cosmic phenomena. Different kinds of light can reveal different features, like warm dust glowing in infrared or energetic gas shining in X-rays. A galaxy might look one way in visible light, a smooth ellipse of stars, but in radio waves it might show jets of material streaming outward from its center. A supernova remnant might be faint in visible light but brilliant in X-rays, as the hot gas from the explosion cools over thousands of years. This multi-wavelength approach is like looking at a landscape in different seasons or different times of day. Each view adds something new, and together they create a fuller sense of place. The observable universe is not the same as all that exists, just all that is reachable by light so far. This is a humbling thought. Beyond the edge of what we can see, there is almost certainly more universe, more galaxies, more stars, more space. Whether that more continues forever or wraps around in some way we don't yet understand is an open question. For now, the observable universe is vast enough to fill our attention, containing hundreds of billions of galaxies, each with billions or trillions of stars, each star a potential sun to planets we cannot yet see. The scale is immense, but it is also knowable, mapped with increasing precision, described in catalogues and databases and images that anyone can explore. This makes the night sky feel like a calm archive, quiet pages of ancient glow. When you step outside on a clear night and look up, you're receiving messages from across space and time, photons that have travelled for years or millions of years to reach your eye. The light from the nearest star beyond our Sun has taken more than 4 years to arrive. The light from the centre of our galaxy has taken about 26,000 years. The light from distant galaxies has journeyed for billions of years, crossing voids and clusters, redshifted by the expansion of space itself, carrying information about an era when the universe was young and still forming its grand structures. With that gentle idea of cosmic postcards in mind, let's wander into how we measure distance without getting overwhelmed by the scale. A light year is a unit of distance, meaning how far light travels in 1 year. Light moves at about 300,000 kilometers per second, or about 186,000 miles per second. In 1 year, that adds up to roughly 9.5 trillion kilometers, or about 6 trillion miles. It's a large number, but it's also a convenient one because it connects the speed of light, a fundamental constant in physics, with the passage of time, which we understand intuitively. Using light years lets astronomers talk about cosmic distances in terms that relate directly to observation. When we say something is 10 light years away, we're also saying we see it as it was 10 years ago. Astronomers also use parsecs, another distance unit that comes from geometry. A parsec is about 3.3 light years, and it arises from a technique called parallax, which measures the tiny shift in a star's apparent position as Earth moves around the Sun. Parallax is similar to how your thumb seems to move against the background when you switch eyes. Hold your thumb up at arm's length, close one eye, then the other, and notice how your thumb appears to jump from side to side against more distant objects. Stars do the same thing, but the shift is tiny because even the nearest stars are enormously far away. By measuring this shift with precision, astronomers can calculate how far away a star is. Parallax works well for nearby stars, within a few hundred light years, but it becomes too subtle for more distant objects. For farther distances, astronomers use standard candles, objects with known brightness. The idea is simple. If you know how bright something truly is, its intrinsic luminosity, you can estimate how far away it is by how dim it looks. This is the same principle you use when you see a distant streetlight at night. If you know all streetlights emit the same amount of light, you can guess which ones are farther away based on which ones appear dimmer. In astronomy, certain kinds of stars and other objects serve as reliable standard candles, their intrinsic brightness known from theory or from careful studies of nearby examples. Certain kinds of exploding stars called Type Ia supernovae can help as standard candles. A Type Ia supernova occurs when a white dwarf star, a dense remnant of a Sun-like star, accumulates matter from a companion star until it reaches a critical mass and undergoes a runaway nuclear explosion. The physics of this process is consistent enough that Type Ia supernovae have remarkably similar peak luminosities. By measuring how bright a Type Ia supernova appears and comparing that to its known intrinsic brightness, astronomers can calculate its distance. This technique has been used to measure distances to galaxies billions of light years away, far beyond the reach of parallax. Another distance clue is redshift, which occurs when light stretches to longer wavelengths as space expands. Imagine light as a wave travelling through space. If space itself is stretching, expanding, then the wavelength of the light stretches too. Longer wavelengths correspond to redder colours in visible light, hence the term redshift. The amount of redshift tells you how much space has expanded since the light was emitted. In a universe where the expansion rate is known, redshift can be translated into distance. This method is especially useful for the most distant objects, where other techniques become impractical. Distance in the universe is often measured with a blend of methods, like a CALM toolkit used step by step. Astronomers build what's called a cosmic distance ladder, with each rung relying on the one below it. Parallax measures nearby stars. Standard candles like Cepheid variable stars, stars whose brightness pulses in a predictable way, extend the ladder farther. Type Ia supernovae reach even greater distances. Redshift carries the ladder to the edge of the observable universe. Each method has its uncertainties, but when they overlap, they confirm and calibrate one another, creating a consistent picture of the universe's scale. Once distance has a soft shape in the mind, we can relax into the universe's slow motion, how space itself gently changes over time. Observations show that the universe is expanding, meaning galaxies tend to be farther apart over time. This discovery emerged in the early 20th century from the work of astronomers who measured the redshifts of distant galaxies and found a pattern. The farther away a galaxy is, the faster it appears to be moving away from us. This relationship, known as Hubble's law, was one of the most profound revelations in the history of science. It suggested that the universe is not static but dynamic, its structure changing on the larger scales. This expansion is not like an explosion into empty space, it's more like space itself stretching. Imagine space as a fabric, a flexible medium that can grow or shrink. As it grows, objects embedded in it, like galaxies, move apart, not because they're racing through space, but because the space between them is increasing. This distinction is subtle but important. Galaxies aren't flying away from a central point. There is no center to the expansion in three-dimensional space. Every observer in the universe, no matter where they are, would see distant galaxies receding, and they would all have the same right to say they're at the center of the expansion. A common picture used to illustrate this is dots on a balloon surface moving apart as the balloon inflates. Imagine drawing several dots on the surface of a deflated balloon, then blowing it up. As the balloon expands, every dot moves away from every other dot. No single dot is special or central. The expansion is uniform. This two-dimensional analogy helps us think about the three-dimensional expansion of space, even though we can't easily visualize a three-dimensional surface expanding in some higher dimension. The balloon model is imperfect. It has an inside and an outside, and it exists in three-dimensional space, but it captures the key idea. Expansion happens everywhere, and there is no edge or center. In that picture, no single dot is the center of the surface's expansion. This is a comforting thought in a way. It means our location in the universe is not special in the large-scale structure. We are not at the center, but neither is anyone else. The universe looks roughly the same from every vantage point, a principle called the cosmological principle. This principle states that on large enough scales the universe is homogeneous, the same everywhere, and isotropic, the same in all directions. Of course, on small scales, the universe is lumpy. There are planets, stars, galaxies, clusters, voids. But if you blur your vision, averaging over hundreds of millions of light years, the lumpiness smooths out into a surprisingly uniform pattern. On the larger scales, the universe looks similar in many directions, a calming idea called the cosmological principle. Observations support this. Maps of the cosmic microwave background, the faint glow of radiation left over from the early universe, show tiny variations in temperature, but overall the sky is remarkably uniform. Surveys of galaxies show that on average the number of galaxies in a large volume of space is about the same, no matter which direction you look. There are local variations, clusters and voids, but the overall distribution is smooth. This uniformity suggests that the laws of physics are the same everywhere, that the universe operates according to consistent rules, and that we can apply what we learn from nearby observations to the distant cosmos. The relationship between distance and redshift helps reveal the expansion pattern. When astronomers plot the distances of galaxies against their redshifts, they see a straight line, at least for relatively nearby galaxies. This linear relationship is Hubble's law. The farther away a galaxy is, the greater its redshift, and thus the faster it appears to be receding. The slope of this line is called the Hubble constant, and it tells us the current rate of expansion. Measuring the Hubble constant precisely has been a major effort in cosmology because it connects to many other important properties, including the age of the universe and its overall geometry. The expansion means very distant light becomes stretched, shifting toward redder wavelengths. For the most distant galaxies we can observe, the redshift is so large that light originally emitted in the ultraviolet has been stretched all the way into the infrared. This makes distant galaxies look fainter and redder than they would if space were not expanding. It also means that certain features in a galaxy's spectrum, patterns of bright or dark lines caused by atoms absorbing or emitting light, are shifted to longer wavelengths, and astronomers can use these shifted patterns to measure the redshift and thus the distance. Expansion also means the universe has a history. It has been different at different times. If galaxies are moving apart now, then in the past they were closer together. If we imagine running the expansion backward, like rewinding a film, the universe becomes smaller, denser, hotter. This backward extrapolation leads to the idea that the universe had a beginning, a moment when the expansion started. That moment is often called the Big Bang, though the name can be misleading. It wasn't an explosion in space, but rather the beginning of space and time themselves. The Big Bang is not a place you could visit. It happened everywhere, because it was the emergence of everywhere as a concept. When scientists talk about the universe being young or old, they mean the age of its expansion history. By measuring how fast the universe is expanding today and how that rate has changed over time, astronomers can estimate how long the expansion has been going on. Current measurements suggest the universe is about 13.8 billion years old. This is the time since the Big Bang, the time during which space has been expanding, matter has been cooling and clumping, and structures like galaxies and stars have been forming. It's a long time by human standards, but in cosmic terms it's just one chapter in a story that might continue indefinitely into the future. Thinking of expansion as slow unfolding can feel peaceful, like a long breath opening a quiet room. The expansion is gradual on human timescales. Over a human lifetime, the expansion of space does not noticeably change the distance between Earth and the Sun, or between stars in our galaxy. Gravity holds these systems together, and the expansion only becomes significant over much larger distances. But over millions and billions of years, the cumulative effect is profound. Galaxies that are now far apart were once close together. The universe that was once hot and dense has become cool and sparse. This slow transformation is gentle, unhurried, a process unfolding over eons. As the universe gently opens outward, we can step into what it's made of, like visiting a calm exhibit of cosmic ingredients. Ordinary matter is the stuff made of atoms, like stars, planets, and people. Atoms consist of a nucleus made of protons and neutrons, surrounded by a cloud of electrons. These particles are subject to the forces of nature, electromagnetism, which binds electrons to nuclei and atoms into molecules, the strong nuclear force, which holds protons and neutrons together in the nucleus, the weak nuclear force, which governs certain kinds of radioactive decay. The arrangement and behaviour of atoms gives rise to chemistry, biology, and all the complexity of the world we experience directly. Most of the matter we touch is built from a small set of particles arranged into atoms. There are about 90 naturally occurring kinds of atoms, each defined by the number of protons in its nucleus. Hydrogen, with 1 proton, is the simplest and most abundant. Helium, with 2 protons, is the second most common. Carbon, nitrogen, oxygen, iron, and other heavier elements make up a smaller fraction of the universe's matter, but they are crucial for forming planets and life. These heavier elements were not present in the early universe. They were created inside stars and dispersed into space through stellar winds and supernova explosions, enriching the gas clouds that eventually formed new generations of stars and planets. Stars shine because they transform matter into energy in their cores. In the intense heat and pressure at a star's centre, hydrogen nuclei fuse together to form helium, releasing energy in the process. This energy works its way outward, eventually radiating into space as light and heat. Nuclear fusion is the source of a star's power, and it's the reason stars can shine steadily for millions or billions of years. The energy released in fusion comes from the conversion of a tiny amount of mass into energy, following Einstein's famous equation, E equals mc squared. Even a small amount of mass, when multiplied by the speed of light squared, corresponds to a tremendous amount of energy. Astronomers have found evidence that much of the universe's matter is dark matter, which does not shine like stars. Dark matter is called dark because it doesn't emit or absorb light in an easy-to-see way. It doesn't glow, it doesn't reflect, it doesn't cast shadows, yet its presence is inferred from its gravitational effects. Galaxies rotate faster than they should if only visible matter were present. Galaxy clusters hold together with a gravitational strength that exceeds what the visible galaxies can provide. The bending of light by gravity, observed in gravitational lensing, often reveals more mass than can be accounted for by stars and gas. We infer dark matter from its gravitational effects on galaxies and galaxy clusters. For example, when astronomers measure the speeds of stars orbiting in a galaxy, they find that stars far from the centre move faster than expected. According to the laws of gravity, If most of the mass were concentrated near the centre where the visible stars are densest, stars farther out should orbit more slowly, but they don't. The observations suggest that galaxies are embedded in large halos of invisible matter, extending far beyond the visible disk or bulge. This dark matter provides the extra gravity needed to explain the observed motions. Another large component in modern models is dark energy, linked to the expansion speeding up. In the late 1990s, astronomers studying distant type Ia supernovae made a surprising discovery. The universe's expansion is not just continuing, it's accelerating. Galaxies are moving apart faster now than they were in the past. This was unexpected because gravity should be slowing the expansion down, not speeding it up. To explain this acceleration, scientists introduced the concept of dark energy, a kind of energy that fills space and exerts a repulsive effect, pushing things apart. Dark energy is a name for an effect we measure, even if we don't fully understand its deeper nature. It might be a property of space itself, a cosmological constant that represents a baseline energy density woven into the fabric of the universe. Or it might be something more dynamic, a field that changes over time. Current observations suggest that dark energy makes up about 68% of the universe's total energy content, dark matter about 27%, and ordinary matter about 5%. These numbers are astonishing. They mean that everything we can see and touch, all the stars and galaxies and planets, represents only a small fraction of what the universe contains. In a gentle way, these names remind us that science can be honest about unknowns. Calling something dark matter or dark energy is not a confession of ignorance, but an acknowledgement of a mystery that drives further inquiry. Scientists don't know yet what dark matter particles are, though they have proposed candidates and are conducting experiments to detect them. They don't know yet what dark energy is, though they are making ever more precise measurements of how the expansion accelerates. This openness to uncertainty is part of the scientific process, and it's a calming reminder that not knowing everything is perfectly acceptable. Even when we don't know everything, the universe still holds its steady, quiet patterns. Gravity still pulls objects together according to well-tested equations. Light still travels at its constant speed. Stars still fuse hydrogen into helium. Galaxies still spiral and cluster. These reliable patterns give us confidence that the universe is comprehensible, that our observations and theories connect to something real and consistent. The unknowns add texture and depth, but they don't undermine the solid ground of what we do understand. With those ingredients in mind, we can drift into the shapes they make: galaxies, clusters, and the soft architecture of the sky. A galaxy is a large collection of stars, gas, dust, and dark matter, bound together by gravity. Galaxies are the basic building blocks of the universe's large-scale structure. They come in many sizes, from dwarf galaxies with a few billion stars to giant elliptical galaxies with trillions. Despite their differences, all galaxies share the same fundamental nature. They are gravitationally bound systems, islands of matter in the vastness of space. Galaxies come in different shapes, including spirals, ellipses, and irregular forms. Spiral galaxies have flat, rotating disks with spiral arms where stars are forming, along with a central bulge of older stars. Elliptical galaxies are more rounded, with stars moving in random orbits rather than organized rotation, and they typically contain older stars with little ongoing star formation. Irregular galaxies lack a clear structure. They're often smaller and have been disturbed by gravitational interactions with other galaxies. These classifications help astronomers organize the diversity they see, though many galaxies show characteristics that blend categories. The Milky Way is a spiral galaxy, and our solar system sits in one of its spiral arms. Our Sun is an ordinary star located about 26,000 light-years from the galactic center, orbiting at a speed of roughly 200 kilometers per second. It takes the Sun about 200 million years to complete one orbit around the galaxy, a galactic year. We live in a disk of stars, gas and dust, and when we look out into the night sky, we see the combined light of billions of stars in that disk, creating a faint glowing band that stretches across the sky. When you see a faint band across the night sky, you may be seeing the Milky Way's dense star regions. From a dark site away from city lights, this band is visible to the naked eye. a soft glow made of countless stars too distant to see individually. Ancient cultures noticed this band and told stories about it, imagining it as a road, a river, or spilled milk. Modern astronomy has revealed it as our view from within a spiral galaxy, looking edgewise through the disk. The light we see is starlight, concentrated in the plane of the disk, dimmed and reddened by intervening dust, but still reaching us after journeys of thousands of light years. Galaxies can gather into groups, like our local group, which includes the Milky Way and Andromeda. The local group contains a few dozen galaxies, most of them small dwarfs, but also including the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy as the largest members. These galaxies are bound together by their mutual gravity, orbiting one another over timescales of billions of years. In a few billion years, the Milky Way and Andromeda are expected to merge, their stars and gas mixing, their shapes transforming, eventually forming a single larger elliptical galaxy. Groups of galaxies can form larger clusters, which are like cosmic towns. A galaxy cluster can contain hundreds or even thousands of galaxies, along with hot gas that fills the space between them and emits X-rays. The galaxies in a cluster move rapidly, their motion sustained by the cluster's deep gravitational well. The hot gas is heated by the energy of galaxy collisions and by the gravitational pull of the cluster itself. Clusters are among the largest gravitationally bound structures in the universe, spanning millions of light years. Clusters can be connected by filaments of galaxies and gas, forming a cosmic web. On the very largest scales, the universe is organized into a network of filaments, walls, and voids. Filaments are elongated structures where galaxies are strung out like beads on a thread. Walls are flatter sheets of galaxies. Voids are large, relatively empty regions where few galaxies are found. This cosmic web is the result of gravity amplifying tiny variations in the distribution of matter that existed in the early universe. Regions that were slightly denser attracted more matter, growing over time, while regions that were slightly less dense became even emptier. The cosmic web is a large-scale pattern, like lace spread gently across space. Mapping this structure requires surveys of millions of galaxies, measuring their positions and distances, plotting them in three-dimensional space. When astronomers do this, the web becomes visible, a delicate tracery of matter, beautiful in its regularity and complexity. The pattern shows that the universe is neither random nor uniform on intermediate scales, but organized by gravity into a repeating motif of filaments and voids. Voids are the quieter regions with fewer galaxies, like calm open patches in the web. A typical void might be 100 million light-years across, containing very few galaxies. Inside a void, the density of matter is lower than average, and the expansion of space is slightly faster. Voids are not completely empty. There are still some galaxies and some gas, but they are much less crowded than filaments and clusters. Studying voids helps astronomers understand the large-scale forces shaping the universe and how matter has redistributed itself over billions of years. This structure shows that the universe is not random chaos, but a slow, patterned tapestry. The cosmic web reflects the initial conditions of the early universe, the influence of gravity over time, and the effects of dark matter and dark energy. It's a pattern that emerged naturally from simple physical laws applied over vast scales and immense durations. The beauty of this pattern lies in its inevitability. Given the starting conditions and the laws of physics, the universe could hardly have done anything else but form this intricate, interconnected structure. If galaxies are the lanterns, then the oldest light is the soft glow behind them, so now we'll visit the universe's gentle afterglow. The cosmic microwave background is faint light spread across the sky in every direction. It is often described as the universe's afterglow from an early, hotter time. About 380,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, the universe was filled with a hot plasma of charged particles that scattered light constantly, making the universe opaque. But once neutral atoms formed, light could travel freely. The radiation that was released at that moment has been travelling through space ever since, stretched by the expansion of the universe from visible and ultraviolet wavelengths into the microwave part of the spectrum. Today this background light is very cool and gentle, mostly visible to special instruments, not to our eyes. The temperature of the cosmic microwave background is about 2.7 degrees above absolute zero, a cold whisper of the universe's hot youth. Telescopes designed to detect microwave radiation can map this glow across the sky, revealing a nearly uniform bath of radiation with tiny temperature fluctuations, about 1 part in 100,000. These fluctuations are the seeds of structure, slightly warmer and cooler patches that correspond to regions where matter was slightly denser or less dense in the early universe. This background light looks remarkably uniform, which supports the idea of large-scale smoothness. The uniformity of the cosmic microwave background is one of the strongest pieces of evidence for the cosmological principle. The idea that the universe is, on average, the same everywhere, no matter which direction we look. The temperature of the background is nearly identical, differing only by those tiny fluctuations. This suggests that the early universe was very smooth and that the processes shaping it acted uniformly across space. Tiny variations in that background contain clues about early structure formation. The pattern of these variations, where the slightly warmer and cooler spots are located, how large they are, how they correlate with one another, tells us about the conditions in the early universe. Cosmologists analyze this pattern using sophisticated statistical techniques, comparing it to predictions from theoretical models. The agreement between observation and theory is remarkable, confirming details about the universe's composition, age, and geometry with high precision. Those small differences helped guide how matter gathered over time. Where the early universe was slightly denser, gravity pulled in more matter, creating regions that would eventually collapse into galaxies and clusters. Where it was slightly less dense, matter drained away, forming voids. The cosmic microwave background gives us a snapshot of these early conditions, a map of the universe when it was young and simple, before stars had formed, before galaxies had assembled, when everything was still smooth and quiet. Studying the background light helps scientists estimate the universe's age and composition. By fitting models to the observed pattern of temperature fluctuations, cosmologists can determine key parameters: the Hubble constant, the density of ordinary matter, the density of dark matter, the density of dark energy, and the overall curvature of space. The precision of these measurements has improved dramatically over the past few decades, thanks to space-based telescopes and ground-based experiments dedicated to mapping the cosmic microwave background in ever greater detail. In a comforting way, it's like a soft echo that still fills the room long after a song began. The cosmic microwave background is a relic, a fossil of the universe's infancy, preserved in the form of light that has travelled across the entire observable universe. It connects us to the earliest moments of cosmic history, a time when the universe was simpler, hotter, denser, and more uniform. Listening to this echo, observing this ancient light, gives us a profound sense of connection to the deep past, and a reminder that the universe has a story, a history that can be read in the light that still surrounds us. The background light also gives a kind of cosmic reference for comparing motion and patterns. Because the cosmic microwave background is so uniform, any motion relative to it shows up as a characteristic pattern. For example, Earth's motion through space creates a Doppler shift in the background. It looks slightly warmer in the direction we're moving toward and slightly cooler in the direction we're moving away from. By measuring this shift, astronomers can determine our velocity relative to the cosmic microwave background, which is effectively the same as our velocity relative to the average rest frame of the universe. This provides a unique reference point, a universal standard of rest. Even the oldest light arrives calmly, with no urgency. Just steady information carried on quiet waves. The cosmic microwave background is patient. It has been travelling for more than 13 billion years, and it will continue to fill the universe for billions of years into the future, though it will grow ever fainter and cooler as the universe expands. There is no rush, no deadline. The information it carries is available to anyone with the right instruments and the curiosity to look. It is a gift from the early universe, a message written in light waiting to be read. With that hush of ancient light in the background, we can lean closer to the idea of time itself, how the universe keeps a slow, reliable rhythm. In modern physics, space and time are woven together into space-time. This idea, developed in the early 20th century by Albert Einstein, transformed our understanding of the universe. Before Einstein, space and time were thought to be separate, independent things. Space was the stage, time was the clock, and neither was affected by the events they contained. but Einstein's theory of relativity revealed that space and time are interconnected, that they respond to the presence of matter and energy, and that measuring them depends on the observer's state of motion. Gravity is described as the curvature of space-time, rather than a simple pulling force. In Newton's view, gravity was a force acting at a distance, somehow reaching across empty space to pull objects toward each other. In Einstein's view, massive objects curve the space-time around them, and other objects move along the straightest possible path through that curved space-time. A planet orbiting a star is not being pulled by a force, it is following a curved path. Through space-time, a path that looks elliptical when we project it into three-dimensional space, but is actually a geodesic, a straight line in the curved geometry of space-time. Massive objects like stars and galaxies curve space-time around them. The more mass an object has, the more it curves space-time. Near the surface of Earth, space-time is very slightly curved, enough to make objects fall at about 9.8 meters per second squared. Near the Sun, the curvature is more pronounced, bending the paths of planets and even the light from distant stars. Near a black hole, the curvature becomes extreme, so steep that not even light can escape once it crosses the event horizon. Light follows the curves of space-time, which can create effects like gravitational lensing. When light from a distant galaxy passes near a massive object like a galaxy cluster, the curvature of space-time bends the light's path. This bending can magnify the distant galaxy, making it appear brighter and larger. It can also create multiple images, arcs, or rings, as light takes different curved paths around the intervening mass. Gravitational lensing is a powerful tool in astronomy, allowing observers to study distant galaxies that would otherwise be too faint to see, and to map the distribution of dark matter based on how it bends light. Gravitational lensing can make distant galaxies look stretched or multiplied, like a soft glass distortion. The images produced by lensing have a dreamlike quality, galaxies smeared into arcs, or repeated around the edges of a massive cluster. These distortions are not illusions, they are real effects of space-time curvature, predicted by Einstein's equations and confirmed by countless observations. They remind us that the universe is not a rigid, fixed backdrop, but a flexible medium shaped by the matter and energy it contains. Time can pass at slightly different rates in different gravitational strengths, called gravitational time dilation, clocks, that are deeper in a gravitational field run more slowly than clocks farther away. This is not a malfunction of the clocks, it is a real property of time itself. An observer near a massive object experiences time passing normally, but when compared to an observer farther away, their clock is running slow. This effect is small in everyday circumstances. On Earth's surface, time runs only slightly slower than at the altitude of a GPS satellite. But the difference is measurable and must be accounted for in technologies that require precise timing. This effect is small in daily life, but it is real and measured in precise systems like GPS. The Global Positioning System relies on signals from satellites orbiting high above Earth, where the curvature of space-time is less pronounced and time runs slightly faster. If engineers did not correct for this time dilation, the system's position calculations would drift by several meters per day, rendering it useless. The fact that GPS works so well is a quiet, everyday confirmation of Einstein's theory, a reminder that relativity is not just abstract mathematics, but a description of how the universe actually behaves. Relativity doesn't make the universe feel unstable. It makes the universe feel consistent in a deeper way. Before relativity, there were puzzles and contradictions between how light behaved and how motion was understood. Relativity resolved those puzzles by showing that the speed of light is the same for all observers, regardless of their motion, and that space and time adjust to preserve this constancy. This adjustment, length contraction, time dilation, the relativity of simultaneity, may seem strange, but it creates a coherent, elegant framework that describes everything from the orbit of Mercury to the behavior of particles in accelerators to the expansion of the universe. One soothing takeaway is that physics is full of rules that keep working, even when the scale changes. The equations of general relativity apply to an apple falling from a tree, to a planet orbiting a star, to light bending around a galaxy cluster, to the expansion of the entire universe. They work across an astonishing range of scales, from meters to billions of light years. This universality is part of what makes physics so powerful and so comforting. The universe is not capricious. It follows rules, and those rules are discoverable, testable, and reliable. The universe can be enormous, yet it still behaves with steady, quiet reliability. No matter how far we look, how deep we probe, the same physical laws apply. Stars in distant galaxies fuse hydrogen into helium just like our sun does. Light from the edge of the observable universe obeys the same speed limit and the same wave properties as light from a nearby lamp. Gravity pulls matter together in distant clusters just as it holds our solar system in place. This reliability is a source of confidence and wonder, a reminder that the universe, despite its vastness and complexity, is understandable. Now we'll step toward the softer edge of knowledge, where scientists offer possibilities and we hold them gently, like clouds that don't need to become anything tonight. Some ideas in physics suggest that our universe might be one of many, sometimes called a multiverse. These ideas are hypotheses, meaning they are possibilities explored by theory, not everyday confirmed facts. They arise naturally from certain interpretations of physical theories, and they are taken seriously by many physicists, but they remain speculative. The evidence is indirect, the predictions hard to test, and the philosophical implications profound. These ideas are hypotheses, meaning they are possibilities explored by theory, not everyday confirmed facts. It's important to distinguish between what is well established and what is speculative. The expansion of the universe is well established. We observe it directly. The existence of dark matter is well supported by multiple independent lines of evidence. The idea of a multiverse, by contrast, is more tentative. It is consistent with some theories. It is suggested by certain mathematical frameworks, but it is not something we have observed directly, and it may never be something we can observe directly. One multiverse idea comes from inflation, a proposed early period of very rapid expansion. Inflation is a theory that was developed to explain certain features of the observable universe, such as why the cosmic microwave background is so uniform and why the universe appears flat. According to inflation, in the first tiny fraction of a second after the Big Bang, the universe expanded exponentially, growing by an enormous factor in an incredibly short time. This rapid expansion smoothed out any initial irregularities and stretched the universe to much larger than the observable portion we can see today. In some versions, inflation could produce separate bubble universes with their own regions of space and time. If inflation is a quantum process, then quantum fluctuations could cause it to end at different times in different places. In regions where inflation ends, a hot, dense, expanding universe like ours begins. But in other regions, inflation might continue, and those regions could spawn their own separate bubble universes. Each bubble would be causally disconnected from the others, expanding into its own space, with its own set of initial conditions. This scenario is called eternal inflation, and it suggests that our universe is just one bubble in a vast, constantly inflating multiverse. Another multiverse idea comes from quantum interpretations that describe different outcomes in different branches. In quantum mechanics, certain processes are described as probabilistic. When you measure a quantum system, you might get one outcome or another, with probabilities determined by the system's quantum state. One interpretation, called the many worlds interpretation, suggests that all possible outcomes actually occur, each in a separate branch of reality. These branches don't interact with each other, so you only ever experience one outcome, but the others exist in parallel. If this interpretation is correct, then the multiverse is not separate bubble universes in space, but separate branches of a single quantum wave function. These interpretations are debated, and thoughtful scientists discuss them carefully. The many worlds interpretation is mathematically consistent and avoids some conceptual problems of other interpretations, but it raises questions of its own. How do we define a branch? What determines when branching occurs? Do these other branches have the same ontological status as the one we experience? These questions do not have agreed upon answers, and different physicists have different views. The debates are ongoing, conducted in journals and conferences, with open minds and mutual respect. Even if other universes exist, they might be hard or impossible to observe directly from here. If bubble universes are separated by regions of eternal inflation, then the space between them is expanding so rapidly that no signal can ever cross from one bubble to another. If quantum branches are separate aspects of a wave function, then by definition they don't interact in a way that allows communication. This means that multiverse ideas, while intellectually interesting, may lie forever beyond the reach of direct empirical confirmation. They remain in a grey zone between physics and philosophy, ideas that enrich our thinking but may never be testable in the usual sense. This is why many multiverse ideas remain philosophical as well as scientific. They touch on deep questions about the nature of reality, the meaning of existence, the role of observation, and the limits of knowledge. They challenge us to think carefully about what counts as evidence, what counts as science, and what counts as a satisfying explanation. They remind us that the universe, and perhaps the multiverse, is stranger and more subtle than our everyday intuition suggest, and that humility is appropriate when we approach the boundaries of what can be known. Wondering about multiple universes can feel like imagining many libraries, interesting but not required for rest. The idea of other universes, other realities, other versions of history can be fascinating during the day, a source of curiosity and speculation. But at night, when the goal is calm and sleep, these ideas need not be urgent. They can be appreciated as possibilities, held lightly, neither insisted upon nor dismissed. They add texture to the landscape of ideas, but they do not change the immediate reality of this room, this breath, this moment. For bedtime, it's enough to know that curiosity can be gentle and uncertainty can be calm. Not all questions need answers. Not all possibilities need to be resolved. The mind can hold mystery without anxiety, can entertain ideas without commitment, can appreciate the open-endedness of the universe without feeling unsettled. This is a skill worth cultivating. The ability to be comfortable with not knowing, to find peace in the presence of unanswered questions, to rest even when the universe still has secrets. And now, like closing a quiet book without finishing every chapter, we'll return to the simplest universe of all. This room, this breath, this steady night. The universe is vast, but your experience of it tonight can be small and safe. You don't need to think about distant galaxies or expanding space or the nature of dark energy. All of that is still there, still real, still quietly unfolding, but it doesn't require your attention right now. Tonight, the universe can be the soft pressure of gravity holding you gently to your bed, the air moving in and out of your lungs, the warmth of your blanket, the darkness behind your eyelids. The air in your room is part of the universe, and it's already doing its job, soft and steady. Oxygen molecules are drifting through the air, finding their way into your lungs, diffusing into your bloodstream, travelling to cells throughout your body where they help release energy from the food you've eaten. Carbon dioxide is following the reverse path carried by blood to your lungs, expelled into the air as you exhale. This exchange happens automatically, without any effort from you, governed by the same physical laws that govern stars and galaxies. The air is patient, reliable, always there, a quiet servant of life. Gravity near you is gentle and familiar, holding everything in place without effort from you. It keeps you resting on your mattress, keeps the blanket draped over you, keeps the air from drifting away into space. Gravity is so constant that you don't notice it most of the time, but it is always working, always present, a background force that creates stability and order. The same gravity that curves space-time around galaxies and bends light around massive clusters is here, acting on you, holding you, anchoring you to Earth, allowing you to rest without floating away. The same physics that guides galaxies also guides the calm fall of a blanket fold. The principles of motion, energy, and force apply just as surely to the soft settling of fabric as they do to the orbit of a planet. When a blanket falls, it moves under the influence of gravity, slowed by air resistance, its shape determined by the tension and flexibility of the fibers. The process is gentle, predictable, governed by laws that are simple at their core, even if the details are complex. There is a deep continuity between the grandest cosmic events and the smallest domestic moments, all of them expressions of the same underlying reality. The night sky doesn't demand attention. It simply offers a quiet view when you want it. If you were to step outside and look up, you would see stars, perhaps the moon, maybe a planet or two. You might see the faint band of the Milky Way if the sky is dark enough. but the sky does not insist. It is not loud or urgent. It is a presence, a backdrop, a source of wonder available whenever you choose to notice it. And if you choose not to notice, if you prefer to keep your eyes closed and turn inward towards sleep, the sky remains patient and unchanging, content to be what it is. Learning about the universe can widen the mind without waking it up. Knowledge of vast distances, ancient light, and cosmic structures can coexist with relaxation. It can deepen a sense of perspective, placing personal worries in the context of a universe that is immensely larger and older than any individual life. This perspective can be calming, not because it makes human life seem insignificant, but because it reminds us that we are part of something larger, something that operates according to regular, reliable principles. The universe does not panic, does not rush, does not collapse under its own weight. It simply continues, steadily, beautifully, according to its nature. The universe has a long history, but you only need this moment. 13.8 billion years have passed since the Big Bang. Countless events have occurred. Galaxies forming, stars igniting, planets coalescing, life emerging. But all of that history has led to this moment. Here, now, with you resting in your bed. You don't need to carry the weight of all that history. You don't need to understand every detail. You don't need to solve every mystery. You only need to be here, breathing, allowing your body to relax, allowing your mind to slow, allowing sleep to approach at its own pace. It's okay to let big questions remain open, like windows with curtains softly drawn. Questions about the nature of dark matter, the fate of the universe, the possibility of other universes, these can wait. They are not urgent. They will still be there tomorrow, or next week, or next year. Tonight, they can rest in the background unanswered but not forgotten, open but not demanding. The mind can hold space for these questions without needing to resolve them right now, just as a window can be open to the night air without needing to let in the full light of day. Rest is one of the most natural things in the universe. Rhythmic, repeating, kind. Every living thing needs rest. Stars have cycles of activity and quiescence. Planets rotate, bringing cycles of day and night. Life has evolved to synchronize with these rhythms, to take advantage of periods of rest for repair, consolidation, and renewal. Sleep is not a failure or a weakness. It is a fundamental part of being alive, as essential as eating or breathing. The universe supports rest, encourages it, provides the conditions for it. Darkness, quiet, stillness, these are not absences but presences, necessary and nourishing. And tonight, you can let the universe be the background while sleep becomes the gentle foreground. All the galaxies, all the stars, all the expanding space, all the ancient light, they can recede into the periphery of awareness. They are still there, still real, still beautiful, but they do not need your conscious attention. What needs your attention now is the sensation of your breath, the weight of your body, the softness of your pillow, the quiet closing of your eyes. Let the universe hold you, support you, surround you with its steady, reliable presence. Let the vastness become a comfort, not a weight. Let the mystery become a lullaby, not a question. Let the night be what it is, a time for rest, a time for sleep, a time to let go. Take a slow inhale, filling your lungs gently, feeling the air come in, and then an even slower exhale, releasing that air, letting it go. And let your thoughts drift outward, quietly, like starlight travelling with no hurry. There is no destination, no urgency, no need to arrive anywhere. Just drift, softly, calmly, into the gentle darkness, into the quiet rest, into sleep. The next story is about to begin. Please relax and enjoy. A black hole is a region in space where gravity has become so extraordinarily strong that past a certain boundary, not even light itself can escape. This might sound dramatic at first, but it's really just a consequence of how gravity works when you concentrate a lot of mass into a very small space. The boundary we're talking about is called the event horizon, and it represents a point of no return for anything trying to escape outward. But before we let that idea feel too heavy, let's remember that black holes are defined by what they do to the space around them, not by having any kind of surface you could stand on or touch. They're more like extremely steep valleys in the fabric of space itself, than physical objects in the traditional sense. The idea of escape is central to understanding black holes, and it all comes down to something called escape velocity. Escape velocity is simply the speed something needs to reach in order to break free from a gravitational pull. Here on Earth, if you throw a ball upward, it eventually falls back down because you haven't thrown it fast enough to escape Earth's gravity. The escape velocity from Earth's surface is about 11 kilometers per second. If you could throw something that fast straight up, it would keep going and never fall back. For a black hole, the escape velocity at the event horizon equals the speed of light, which is about 300,000 kilometers per second. Since nothing can travel faster than light, nothing that crosses the event horizon can ever come back out. Now, outside the event horizon, gravity behaves just like normal gravity. It's strong, certainly, but it's not magical or mysterious. The same rules apply that govern how planets orbit stars or how moons orbit planets. A black hole doesn't somehow turn off the laws of motion that Isaac Newton discovered centuries ago. Objects still follow predictable paths based on their speed and the gravitational pull they experience. This is important to keep in mind because black holes are often imagined as cosmic vacuum cleaners that devour everything around them, but that's not really how they work at all. Black holes are often described by just a few properties. The main ones are mass, spin, and electric charge. These three numbers can tell you almost everything about how a black hole will affect the space around it. In the real universe, most astrophysical black holes are expected to have almost no net electric charge. This is because space contains roughly equal amounts of positive and negative charges, and any imbalance would quickly be neutralized. So in practice, we usually only worry about mass and spin when we're thinking about actual black holes out there in the cosmos. Many black holes are thought to spin, and this makes sense when you consider how they form. The stars and clouds of gas that collapsed to create them were already spinning, because almost everything in space rotates to some degree. When something collapses and becomes much smaller, it spins faster, just like a figure skater pulling in their arms during a pirouette. So the black holes we find in nature likely inherited their rotation from whatever made them, carrying that motion forward even after the original object has been completely transformed. The concept of spin in a black hole is actually quite fascinating when you pause to think about it. Unlike a spinning top or a rotating planet, a black hole doesn't have a surface that's visibly moving. Instead, its spin is encoded in how it drags space-time around with it. This effect, called frame dragging, means that space itself near a rotating black hole is being pulled along in the direction of the rotation. If you tried to remain stationary near a spinning black hole, you'd find yourself being swept along despite your best efforts, like trying to stand still in a flowing river. The faster the black hole spins, the stronger this dragging effect becomes, and the more it influences the behavior of anything nearby. Now let's drift gently into the question of how black holes form in the first place. Many black holes form when very massive stars run out of fuel and can no longer support themselves against their own gravity. Stars shine because nuclear fusion in their cores releases energy, and that energy creates an outward pressure that balances the inward pull of gravity. It's a delicate equilibrium that can last for millions or even billions of years depending on the star's size. But all stars eventually exhaust their fuel supply, and when fusion slows down, gravity begins to win the tug of war inside the star. The journey of a massive star is actually quite long and involves several stages of fusion. A star begins by fusing hydrogen into helium, which is the process that powers our sun, and will continue to do so for another 5 billion years or so. When the hydrogen in the core runs out, the core contracts and heats up until it's hot enough to fuse helium into heavier elements like carbon and oxygen. More massive stars can continue this process, fusing progressively heavier elements in their cores. Carbon fuses into neon and magnesium, then oxygen, then silicon, each stage producing heavier elements and releasing energy that keeps the star inflated against gravity's pull. But this process can't continue forever. Each successive stage of fusion releases less energy and burns through its fuel faster. A star might spend millions of years burning hydrogen, but only a few years burning carbon, and mere days or hours burning silicon. Eventually, the core fills with iron, and here the process stops. Iron is special because fusing it doesn't release energy. It actually requires energy. So when a massive star develops an iron core, there's no more fusion to provide outward pressure. The core has reached the end of the line. What happens next is both violent and strangely orderly. The core of the star collapses inward very rapidly, sometimes in less than a second. The iron atoms are crushed together with such force that protons and electrons combine to form neutrons, releasing vast numbers of neutrinos in the process. The core becomes incredibly dense, and when it can't be compressed any further, it rebounds slightly. This rebound sends a shockwave racing outward through the star's outer layers. That shockwave, reinforced by energy from the escaping neutrinos, blasts the outer layers into space in what we call a supernova. These explosions can briefly outshine entire galaxies, releasing tremendous amounts of energy in just a few seconds. But despite all that drama, a black hole itself is not an explosion. It's a compact outcome of collapse, a region where gravity has compressed matter so tightly that the usual rules about solids, liquids, and gases no longer apply. The leftover core from the supernova can become either a neutron star or a black hole, depending on how much mass remains after the explosion. If the core's mass is below a certain threshold, usually estimated at around 2 to 3 times the mass of the Sun, it becomes a neutron star. These objects are extraordinarily dense, packing more mass than the Sun into a sphere only about 20 kilometers across. But they can support themselves through something called neutron degeneracy pressure. If the core is more massive than that threshold, however, not even neutron degeneracy pressure can halt the collapse. Gravity overwhelms every form of resistance, and the core continues shrinking, passing through the point where it becomes a black hole. There's no known force in physics that can stop this collapse once it begins, at least not according to our current understanding. The matter doesn't settle into a new stable configuration. It simply keeps contracting, disappearing behind its own event horizon. Most stellar mass black holes, the kind that form from individual stars, are somewhere between a few times and a few dozen times the mass of the Sun. Stars' initial mass doesn't translate directly into black hole mass, though, because stars lose material over their lifetimes. They shed gas through stellar winds, powerful streams of particles flowing away from the star's surface. Very massive stars can lose significant fractions of their mass this way, carried off by the intense radiation pressure from their cores, and of course a lot of mass gets blown away during the supernova itself. So even a star that started out with 50 times the Sun's mass might leave behind a black hole of only 10 or 20 solar masses. Some black holes may form through what's called direct collapse, which involves a quieter stellar ending. In this scenario, the star's core collapses without producing a bright supernova. The outer layers might fall back onto the core rather than being ejected, and the whole process happens more subtly. This might occur if the star is so massive and its core so large that the supernova mechanism fails to blow off the outer layers. Instead of exploding outward, everything just falls inward, and the star disappears from view, swallowed by the black hole it becomes. We're not entirely sure how common this process is, but it may explain some of the more massive stellar black holes we've detected. We think black holes have been forming throughout cosmic history, ever since the first generation of massive stars lived and died billions of years ago. Those first stars, called population 3 stars, formed from the primordial hydrogen and helium created in the Big Bang. Without heavier elements to help them radiate energy efficiently, they may have grown to enormous sizes, hundreds of times the mass of the Sun. When these giants died, they could have left behind black holes more massive than any stellar remnant we see forming today. Some of these ancient black holes might still be out there, drifting through space, silently marking where the universe's first stars once shone. And black holes can grow after they form, too. They can absorb gas and dust from their surroundings, or they can merge with other black holes, gradually increasing in mass over time. Each bit of matter that falls in adds to the black hole's mass and slightly increases the size of its event horizon. The relationship is linear. Double the mass, and you double the radius of the event horizon. This is different from most objects, where doubling the mass might only increase the radius by a factor of about 1.26, the cube root of 2. But for black holes, the event horizon radius grows in direct proportion to mass, which is one of the many unusual features these objects possess. One of the most comforting facts about black holes is that they don't behave like cosmic vacuum cleaners at all. Far from a black hole, gravity depends mainly on mass, just like it does for any other object. If you were to magically replace the Sun with a black hole of exactly the same mass, Earth's orbit would stay almost the same. We wouldn't get pulled in or flung away. What would change is the extreme gravity very close to where the Sun used to be. But out here at Earth's distance, roughly 150 million kilometers away, things would continue much as before. We'd lose the sunlight, of course, which would be unfortunate for entirely different reasons, but gravity wouldn't suddenly reach out and grab us. This is because gravity follows an inverse square law. The strength of gravity decreases with the square of the distance. If you double your distance from an object, the gravitational pull becomes 1/4 as strong. If you triple the distance, it becomes 1/9 as strong. This law applies to black holes just as it does to stars, planets, and every other massive object. At large distances, you simply can't tell whether a mass is concentrated in a black hole, spread out in a star, or distributed in any other way. The gravitational field depends only on the total mass and how far you are from it. Objects aren't pulled into black holes unless they get on a path that brings them too close. Orbiting safely is entirely possible at distances well outside the event horizon. In fact, many things in space orbit black holes just as comfortably as planets orbit stars. In space, the difference between falling and orbiting often comes down to sideways speed. If you're moving fast enough sideways, you keep missing the object you're falling toward, and that's what an orbit is. It's really just continuously falling while also continuously missing. The Moon orbits Earth this way, falling toward our planet but moving sideways fast enough that it keeps missing, circling us month after month, year after year. Accretion, the process by which black holes gather material, happens when gas loses energy and spirals inward. This might occur through friction with other gas, or through interactions with magnetic fields, but it's not because everything in the vicinity gets instantly dragged in. Gas in space often carries some amount of rotation, some angular momentum. As gas falls toward a black hole, conservation of angular momentum causes it to spiral rather than plunge straight in. It's the same principle that makes water spiral down a drain, or causes air to rotate in a hurricane. The gas forms a disk around the black hole, and only gradually through friction and magnetic interactions does it lose enough energy to fall closer and closer to the event horizon. Many black holes spend long periods in a quiet state, barely interacting with anything at all. Space is huge and mostly empty, and the distances between objects are so vast that most things never come anywhere close to a black hole. The nearest known black hole to Earth is probably at least a few hundred light years away, and even stellar mass black holes within our galaxy number only in the hundreds of millions at most, spread across a disk 100,000 light years across and several thousand light years thick. The odds of randomly encountering one are vanishingly small. Rather than thinking of black holes as hungry mouths waiting to devour everything, it's better to imagine them as deep gravitational valleys. If you stay on the gentle slopes far from the center, you're perfectly safe. It's only if you venture too close to the steep sides and lose your footing, so to speak, that you'd have trouble getting back out. And even then, too close usually means within a few times the event horizon radius, not thousands or millions of kilometers away. The danger zone around a black hole is surprisingly small compared to the vast distances of space. With that calm understanding in place, we can move into the question of how scientists actually know black holes exist. After all, a black hole itself emits no light from inside the event horizon. By definition, nothing that crosses that boundary comes back to tell us about it. But the area around a black hole can glow very brightly if gas happens to be falling in, and that gives us one of our best clues. Even more importantly, we can watch stars orbit something invisible but extremely massive, and that reveals the hidden presence of a black hole. This technique has been used most famously at the center of our own Milky Way galaxy. Astronomers have tracked individual stars as they swing around an invisible object over the course of many years. Some of these stars move at speeds of thousands of kilometers per second, completing their orbits in just a few years despite being many billions of kilometers from the central point. By measuring how fast these stars move and the shapes of their orbits, scientists can calculate the mass of whatever they're orbiting using Kepler's laws of planetary motion, the same mathematical relationships that describe how planets orbit the Sun. In the case of the Milky Way's center, the numbers point to something with about 4 million times the mass of the Sun packed into a region smaller than our solar system. There's no known object other than a black hole that could fit those criteria. A cluster of normal stars with that much mass would be far larger and would emit plenty of light. A cluster of neutron stars or white dwarfs would be unstable and would quickly collapse or disperse. Only a supermassive black hole can be that massive and that compact, while remaining stable over millions of years. The evidence has accumulated over decades. In the 1990s, astronomers began tracking a star called S2, which orbits the Milky Way's central black hole every 16 years. As telescope technology improved, they were able to watch S2 complete multiple orbits, refining their measurements of the central mass with each pass. In 2018, S2 made its closest approach, coming within about 17 light-hours of the black hole, moving at nearly 3% of the speed of light. Observations during this close approach allowed astronomers to test general relativity in the strong gravitational field near the black hole, and the theory passed with flying colours. In other systems, gas pulled from a companion star heats up as it falls toward a compact object, and that heat causes it to shine in X-rays. This happens in what we call X-ray binary systems. Imagine a normal star and a black hole orbiting each other. If they're close enough, the black hole's gravity can pull gas away from the outer layers of the normal star. This gas doesn't fall straight into the black hole. Instead, it forms an accretion disk, spiralling around the black hole while gradually moving inward. Friction within the disk heats the gas to millions of degrees, hot enough that it radiates primarily in X-rays rather than visible light. X-ray telescopes in space can detect this radiation, revealing the presence of something small and dense. By studying the orbital motion of the visible star, astronomers can estimate the mass of its unseen companion. If the compact object is too massive to be a neutron star, which has its own upper mass limit of roughly 2 to 3 solar masses, then it's almost certainly a black hole. This method has helped astronomers catalogue dozens of black hole candidates in binary star systems throughout our galaxy. Each discovery adds another data point to our understanding of how black holes form, how common they are, and how they behave. Another beautiful clue comes from gravitational lensing, the way gravity bends light. According to Einstein's theory of general relativity, massive objects curve the space around them, and light follows that curvature. The effect is a bit like looking through a bent piece of glass or a curved lens. Light from a distant galaxy can be magnified and distorted by a massive object between us and that galaxy, and sometimes the lensing pattern points to extremely compact objects, possibly black holes. In some cases, gravitational lensing creates multiple images of the same background object, arranged in arcs or even complete rings around the lensing. Mass. These configurations are called Einstein rings, and they occur when the background object, the lens, and the observer are almost perfectly aligned. The symmetry is striking and beautiful, a reminder that even in the depths of space, mathematical elegance emerges from physical law. By studying the detailed shapes and brightness of these lensed images, astronomers can infer properties of the lensing object, including whether it might be a black hole. We've even detected microlensing events where a black hole passes in front of a background star, briefly brightening it in a characteristic way. The black hole's gravity acts like a magnifying glass, focusing the star's light toward us and making it appear temporarily brighter. The brightening follows a specific pattern over time, rising smoothly to a peak and then fading symmetrically. By analysing this light curve, astronomers can estimate the mass of the lensing object and in some cases determine whether it's likely to be a black hole rather than a normal star or other object. More recently, black holes have been detected through gravitational waves, which are ripples in space-time itself. When two black holes spiral together and merge, they release a tremendous amount of energy in the form of these waves, which spread outward at the speed of light. On Earth, detectors like LIGO and Virgo use laser beams bouncing between mirrors several kilometers apart to measure the incredibly tiny stretches and squeezes in space caused by passing gravitational waves. Each detection is like hearing the universe ring like a distant bell, quietly announcing events that happened millions or billions of years ago in galaxies far away. The first detection of gravitational waves came in September 2015, a century after Einstein first predicted their existence. The signal came from two black holes, each about 30 times the mass of the Sun, that had spiraled together and merged about 1.3 billion light-years away. The event released more energy in a fraction of a second than all the stars in the observable universe combined emit as light over the same time period. Yet the effect on Earth was minuscule, changing lengths by less than 1/10,000th the diameter of a proton. It's remarkable that we can detect something so small, and it speaks to both the precision of the instruments and the dedication of the scientists who built them. Since that first detection, LIGO and Virgo have observed dozens more black hole mergers, along with mergers of neutron stars and mixed systems where a black hole merges with a neutron star. Each event provides new information about the population of compact objects in the universe. We've learned that black holes can be more massive than we expected based on stellar evolution models, suggesting that either stars can collapse into more massive black holes than we thought, or that black holes can grow substantially after they form through mergers or accretion. Now let's float a bit, closer, still safely, and look at the elegant structures that form around black holes. One of the most important is the accretion disk, a swirling disk of gas and dust that orbits the black hole. As material spirals inward, friction between neighbouring bits of gas and the compression from gravity heat everything up. The temperature can climb so high that the disk shines in ultraviolet and X-ray light. This brightness doesn't come from inside the black hole itself, which remains dark. Instead, it comes from the material outside the event horizon, radiating away energy as it falls. The structure of an accretion disk depends on several factors, including how much material is falling in and how viscous the gas is. Some accretion disks are thin and flat like a cosmic pancake, with most of the mass concentrated in a narrow layer. These thin disks are relatively cool and radiate efficiently, converting gravitational potential energy into light as the gas spirals inward. Other disks are puffier and more chaotic, with hot gas swirling in complicated three-dimensional patterns. These thick disks might occur when the infall rate is very high, so much gas is falling in that radiation pressure puffs up the disk and makes it less efficient at radiating energy. The inner part of a disk can orbit extremely fast, sometimes at speeds approaching the speed of light. This happens because the closer you get to the black hole, the stronger the gravity, and orbital speed increases to balance that pull. Near the innermost stable circular orbit, gas is moving at a substantial fraction of light speed, whipping around the black hole many times per second. It's a mesmerizing dance of matter and energy, all orchestrated by the invisible hand of gravity. Some black holes also produce jets, which are narrow beams of particles shooting outward at tremendous speeds, sometimes nearly the speed of light. These jets can extend for thousands or even millions of light years, far beyond the galaxy. Hosting the black hole, they're launched by complicated interactions between the black hole's rotation, the magnetic fields threading through the accretion disk, and the immense energies involved. The exact mechanism isn't fully understood, but it seems to involve magnetic fields being twisted and amplified by the rotating disk and black hole, eventually flinging particles outward along the rotation axis. Even though jets sound dramatic, they can be described peacefully as cosmic fountains, just physics in motion. They're not weapons or dangers, merely another way energy and matter flow in the universe. Jets can interact with the gas in and around galaxies, heating it and stirring it, potentially influencing star formation over vast regions. In some cases, jets carve out huge bubbles in the intergalactic medium, regions where hot gas has been pushed aside by the jet's pressure. These bubbles can persist for millions of years, slowly expanding and fading as the jet that created them shuts off or redirects. It's worth noting that many black holes have no bright disk at all, at least not right now. If there's no gas nearby to feed the black hole, it simply sits there quietly, invisible except for its gravitational influence. This is the state of most black holes most of the time. The universe is full of these silent objects waiting patiently for the chance arrival of new material to devour. They might wait millions or billions of years between meals, spending the vast majority of their existence in dark dormancy, not interacting with anything, not emitting any radiation, just being gravitational wells in the fabric of space-time. Let's widen our view again and turn our attention to the supermassive black holes that sit at the centres of galaxies. Many galaxies, including our own Milky Way, appear to have one of these giants anchoring their core. Supermassive black holes can be millions to billions of times the mass of the Sun. The Milky Way's central black hole, called Sagittarius A, pronounced A-star, is relatively modest by supermassive standards, at about 4 million solar masses. We know it's there because of those fast-moving stars we mentioned earlier, whipping around an invisible point at speeds that would make our heads spin. Other galaxies host even larger black holes. The galaxy M87, about 55 million light-years away, contains a black hole with a mass of about 6.5 billion solar masses. This is the black hole that was imaged by the Event Horizon Telescope in 2019. producing the first direct visual evidence of a black hole's shadow. The image shows a bright ring of emission surrounding a dark central region, exactly as predicted by general relativity. The dark region is larger than the event horizon itself, because light can orbit the black hole several times before escaping, creating a zone called the photon sphere where the black hole's shadow extends. Even supermassive black holes can be surprisingly calm when they aren't actively consuming material. A galaxy can look perfectly peaceful and serene while its central black hole quietly sits in the middle, exerting its gravitational influence but not drawing much attention. However, when a supermassive black hole does have access to a lot of gas, it can power what's called a quasar. Quasars are among the brightest objects in the universe, shining with the light of trillions of stars. The name quasar comes from quasi-stellar radio source, because when they were first discovered in the 1960s, they looked almost like stars in optical images but emitted strong radio waves, which was unusual. We now know that quasars are the brilliant cores of distant galaxies, powered by supermassive black holes actively feeding on gas. The gas forms an accretion disk around the black hole, and the disk becomes so hot and bright that it outshines all the stars in the galaxy combined. Quasars were much more common in the early universe when galaxies were still young and gas-rich, going through their most active phases of star formation and black hole feeding. Looking at distant quasars is like looking back in time, seeing the universe as it was billions of years ago when galaxies were more violent and chaotic than they are today. The energy released by feeding supermassive black holes can have a profound influence on their host galaxies. Radiation and jets can heat the surrounding gas, sometimes preventing it from cooling down and forming new stars. This feedback effect can regulate the growth of galaxies over cosmic time, limiting how large they become. Without this regulation, galaxies might continue forming stars and growing indefinitely, but the energy from their central black holes puts a brake on the process. It's a slow, steady interplay between destruction and creation, between gathering and dispersing, a conversation between black holes and galaxies that unfolds over hundreds of millions of years. Most of the time, galaxies and their central black holes exist in a kind of quiet balance, neither growing rapidly nor shutting down entirely, just persisting in a long cosmic equilibrium. The black hole's mass tends to correlate with properties of the galaxy's central bulge, the dense concentration of stars near the center. More massive bulges tend to host more massive black holes, suggesting that black holes and galaxies grow together over time, influencing each other's evolution in subtle ways. This relationship is still not fully understood, and it's an active area of research in astrophysics. From the grand scale of galaxies, let's drift into the gentle strangeness of space-time itself, and how time and light behave near strong gravity. In Einstein's general theory of relativity, gravity isn't really a force in the traditional sense. Instead, it's the result of mass and energy curving the fabric of space-time. Imagine space-time as a flexible sheet, and massive objects as weights placed on that sheet. They create dips and curves, and other objects moving across the sheet naturally follow those curves. This is why planets orbit stars and why light bends near massive objects. The curvature of space-time is everywhere, all around us, even right here on Earth. But it's so slight in most places that we don't notice it directly. It takes extremely sensitive measurements to detect the curvature caused by Earth's mass, or even the Sun's mass. Near compact objects like neutron stars and black holes, however, the curvature becomes extreme. Space-time is bent so sharply that the usual separation between space and time starts to blur. Directions that look purely spatial from far away can acquire a time-like character close to the event horizon. Near stronger gravity, time itself passes differently compared to regions farther away. This effect is called gravitational time dilation, and it's not just theoretical. We measure it and account for it in practical technology. The GPS satellites orbiting Earth experience slightly weaker gravity than we do on the surface, and so time runs a tiny bit faster for them than for us. If we didn't correct for this difference, GPS coordinates would drift and become inaccurate within minutes. The correction is small, about 38 microseconds per day, but over time it accumulates and would make GPS navigation useless without accounting for it. The effect is subtle in everyday life, but it grows dramatically near massive, compact objects like black holes. Close to a black hole, the difference in time flow becomes extreme. If you could watch someone falling toward a black hole from a safe distance far away, you'd see them appear to slow down as they approach the event horizon. Their movements would seem to stretch out in time, and light from them would become redder and dimmer. This isn't an illusion or a trick of perception. It's a real effect of how time runs differently in different gravitational fields. From the perspective of the falling person, however, everything feels normal. Time passes for them just as it always has. They continue to experience seconds ticking by at a regular rate, right up until they cross the event horizon and beyond. They wouldn't notice anything special happening at the event horizon itself. There's no barrier to feel, no sudden change in their experience. Only later, if they tried to send a signal back out and found that it could never escape, would the significance of the crossing become apparent. But by then, of course, it would be too late to turn back. Light leaving a deep gravitational well loses energy in the process, and this energy loss shifts the light toward redder wavelengths. This phenomenon is called gravitational redshift. The deeper the well, the more pronounced the shift. Light climbing out from near a black hole's event horizon would be severely redshifted, appearing dimmer and stretched compared to how it looked when it was emitted. The closer you get to the event horizon, the stronger these effects become until right at the horizon itself, light trying to escape is essentially frozen in place, never quite making it out, its energy redshifted to zero as observed from far away. This interplay between space, time, and light creates some of the most beautiful and strange predictions of general relativity. From far away, infalling objects seem to slow and freeze at the event horizon, never quite crossing it from the outside observer's point of view. But from the object's own reference frame, the journey continues smoothly and steadily. There's no barrier to notice, no sudden change. The event horizon is simply a mathematical boundary that marks the point where escape becomes impossible, not a physical wall or membrane. It's defined by outward light rays that are trying to escape but making no progress, held in place by the intense gravity. With space-time feeling a bit softer and stranger, we can explore what are sometimes called the safe distances around black holes, and where things start to become unstable. There's a region outside a black hole where stable circular orbits stop being possible. This boundary is often called the innermost stable circular orbit, abbreviated ESCO. The exact location of the ISCO depends on the black hole's spin. For a non-rotating black hole, it's at 3 times the radius of the event horizon, which is about 6 times the mass of the black hole, measured in units where the speed of light and Newton's gravitational constant are set to 1. For a rapidly spinning black hole, it can be closer, because the rotation drags space-time around with it and allows stable orbits nearer to the centre. Outside the ISCO, matter can orbit in relatively stable paths, much like planets orbit the Sun. You could, in principle, orbit a black hole indefinitely at these distances, going round and round without falling in. Objects in stable orbits don't need any thrust or propulsion to maintain their position. They're simply following the natural curvature of space-time, coasting along geodesic paths the way planets have orbited stars for billions of years. Inside the ISCO, however, things change. Any small disturbance, like friction with other orbiting material, or a slight slowdown from emitting radiation, will cause an object to lose energy and plunge inward more rapidly. This is why the inner edge of an accretion disk often sits near the ISCO. Material closer than that doesn't have time to orbit many times. It simply spirals in quickly and crosses the event horizon. The transition can be quite sharp. Outside the ISCO, gas moves in nearly circular orbits, slowly drifting inward over many revolutions. Inside the ISCO, gas plunges almost radially, falling toward the black hole in a small fraction of an orbit. This creates a natural edge to the accretion disk, a place where the bright emission from the disk cuts off relatively suddenly. The event horizon itself is not a solid wall or a surface you could touch. It's just a boundary defined by the mathematics of escape. If you were to fall through it, you wouldn't feel anything special at that exact moment. No jolt, no barrier, no sign that you'd passed the point of no return. Only later, when you tried to turn around and found you couldn't, would the significance of the crossing become apparent. And beyond the event horizon, at the very centre of the black hole, classical general relativity predicts something called a singularity, a point where density becomes infinite and the curvature of spacetime becomes extreme. But many scientists expect that quantum physics will change our understanding of what really happens at that extreme centre. Quantum mechanics and general relativity don't currently fit together perfectly, and singularities are places where our current theories break down. Quantum effects, which are negligible in most everyday situations and even in most astrophysical contexts, might become important at the incredible densities and curvatures expected inside black holes. Some theories suggest that quantum effects might prevent the formation of a true singularity, replacing it with a region of extremely high but finite density. So some of the scariest sounding terms in black hole physics, like singularity, are really placeholders for regions where we don't fully understand the physics yet. They mark the boundaries of our current knowledge, places where our best theories point to something strange happening but can't give us a complete picture. And there's something soothing about not knowing everything, because it means the universe still works, still follows consistent rules, even when our models reach their limits. We can observe, measure, and predict black hole behavior very accurately, without needing a complete theory of quantum gravity. The uncertainty lies at the very center, in a region that's inaccessible to observation, and likely to remain so. Next, let's move into the quiet evidence that black holes can collide and merge, making ripples that pass through the universe like the beat of a soft, distant drum. When two black holes orbit each other, they form what's called a binary system. These binaries might form when two massive stars in a binary system both undergo supernovae and leave black holes behind, or when black holes in a dense stellar environment like a globular cluster encounter each other and pair up. Over time, they gradually lose energy by emitting gravitational waves. These waves carry away momentum and energy, causing the orbit to shrink. The two black holes spiral closer and closer together, slowly at first, then faster and faster as they approach. The inspiral phase can last for billions of years if the black holes start out far apart, but it accelerates dramatically in the final moments. When the black holes are far apart, the gravitational waves they emit are weak, and the orbit shrinks very slowly. But as they move closer, the waves become stronger, carrying away more energy per orbit, and the spiraling speeds up. In the last few minutes before merger, the black holes might be orbiting each other hundreds of times per second, releasing enormous amounts of energy in gravitational waves. Finally, they merge, and in that instant they combine into a single black hole, releasing more energy than all the stars in the observable universe emit as light during that same brief moment. Yet despite that tremendous output, the merger itself is silent and invisible to our eyes. We only know it happened because detectors like LIGO can measure the gravitational waves that spread outward at the speed of light. These waves are not sound, and they're not electromagnetic radiation like light or radio waves. They're ripples in the fabric of space-time itself, tiny stretches and squeezes that alternately compress and expand distances. When a gravitational wave passes through Earth, it causes the distance between objects to oscillate very slightly, stretching space in one direction while compressing it in the perpendicular direction, then reversing the pattern. LIGO detects this using laser beams bouncing between mirrors placed several kilometers apart. By measuring changes in the light's travel time, scientists can detect shifts smaller than the width of a proton, far smaller than an atomic nucleus. It's an extraordinary feat of engineering and precision. The detectors have to be isolated from every conceivable source of vibration and noise. They're built in remote locations and suspended on elaborate systems designed to filter out seismic vibrations, temperature fluctuations, and even quantum noise in the laser light itself. The signals are incredibly faint by the time they reach Earth, which is why the detectors must be so sensitive. They have to filter out vibrations from earthquakes, passing trucks, ocean waves, and countless other sources of noise. Even things like lightning strikes thousands of kilometers away, or timber being harvested in nearby forests can create signals that might be confused with gravitational waves. But when the data is carefully analysed, the signature of a black hole merger stands out clearly. It produces a characteristic pattern called a chirp, a rapid increase in frequency and amplitude as the black holes spiral together, followed by a sudden cut-off when they merge and the ring down as the newly formed black hole settles into its final state. Each detection helps us learn how common black holes are, how they form in different environments, and what the population of black holes throughout the universe looks like. Some of the mergers involve black holes with masses larger than expected from typical stellar evolution, suggesting that there may be multiple pathways for black holes to form and grow. Perhaps some black holes form from the direct collapse of massive stars without a bright supernova. Perhaps some grow through repeated mergers in dense star clusters. Perhaps the early, universe-produced black holes through different mechanisms that aren't operating anymore. In a calm, almost poetic way, gravitational waves are the universe telling us about events we could never witness directly. They let us listen to the cosmos in a new way, hearing the gentle geometry of space-time responding to violent but distant events. Each wave that passes through us is a messenger from the past, carrying information across billions of light years, arriving just in time for us to measure and understand. The waves pass through everything, through Earth, through our bodies, through the air, unimpeded and unnoticed except by the most sensitive instruments we can build. As we near the end of this journey, let's return from the cosmic scale back to the bedside scale, where gravity is holding you steadily and nothing is asking you to chase the stars tonight. Black holes are far away, unimaginably far in most cases, and space is so vast that their influence barely reaches us. Your night is safely ordinary, wrapped in the familiar gravity of Earth, which pulls gently and constantly at every part of you, keeping you grounded and still. The gravity near you is not mysterious or strange. It's the same force that makes apples fall from trees, that keeps the moon orbiting Earth, and that gathers rain from clouds. The same fundamental physics that shapes black holes also shapes raindrops as they fall, the rolling motion of ocean waves, and the steady rhythm of your breathing. Gravity is universal, connecting the smallest scales to the largest, from the air in your lungs to the galaxies spinning in deep space. It operates on the same principles everywhere, following the same mathematical laws, whether it's holding you to your bed or holding together a cluster of galaxies. Black holes remind us that the universe can be dramatic and extreme without being personal or threatening. They exist in their own distant corners of space-time, following the rules laid out by physics, neither caring about us nor seeking us out. Most black holes spend most of their time quiet and undisturbed, not feeding, not merging, just sitting in the dark, patiently being what they are. There's a kind of peacefulness in that steadiness, in knowing that even the most extreme objects are bound by consistent, understandable laws. They're not capricious or angry or hungry in any emotional sense. They simply do what gravity compels them to do, warping space-time around them, waiting in their deep gravitational wells. The light you see when you look up at the night sky is often ancient, having travelled for years or even millennia before reaching your eyes. Photons from distant stars set out on their journey long before you were born, crossing the empty gulf of space at steady, unchanging speed, arriving calmly to paint the sky with faint points of light. Some of that light left its source when humans were just learning to farm, or when dinosaurs walked the Earth, or even before our solar system existed. The universe is patient. It moves on timescales that dwarf human lifetimes, and most cosmic events unfold slowly, gradually, over millions or billions of years. Even the most extreme objects in space fit into long, slow cosmic rhythms. Stars are born in collapsing clouds of gas, burn steadily for eons as they fuse hydrogen into helium and heavier elements, and eventually die, either fading quietly or exploding dramatically depending on their mass. Galaxies drift through space on journeys that span billions of years, sometimes colliding and merging over hundreds of millions of years in slow-motion cosmic dances that reshape their structures. Black holes grow imperceptibly slowly most of the time, one small mouthful of gas at a time, or wait in silence for another black hole to find them across the vast distances of space. There's no rush, no urgency. The universe has all the time it needs, more time than our minds can really grasp. Learning about black holes doesn't pull you into them or put you at risk. It simply lets your mind widen for a moment, stretching to encompass ideas that are grand and strange and beautiful. You can think about event horizons and gravitational waves, about space-time curvature and the inspiral of binary black holes, and then let those thoughts go, releasing them back into the quiet as you settle down to rest. Knowledge doesn't weigh you down. It can actually lighten the mind, replacing vague fears with clear understanding, turning the unknown into the known, transforming mystery into comprehensible physics. Tonight, you don't need to solve the mysteries of the universe. You don't need to calculate orbits or measure gravitational waves or understand every detail of general relativity. You only need to rest inside the universe, which is vast enough to hold everything, including you and your small, safe corner of it. The cosmos doesn't require your attention or your effort. It will continue its slow, majestic, unfolding whether you're awake or asleep, thinking or dreaming, wondering or simply being. As you relax into your bed, you can let gravity do what it has always done. It holds you steady against the mattress, pulls the blankets softly down around you, and keeps the air settled in your room at just the right pressure for breathing. Gravity is the reason your body feels heavy and comfortable, why you can sink into stillness without effort, why relaxation feels like letting go and allowing yourself to be held. It's always there, always reliable, always working in the background to keep everything in place, from the smallest dust particle to the largest galaxy cluster. The black holes are far away, separated from us by distances so vast that light takes years, centuries, or millions of years to cross them. The stars are steady in their courses, following orbits determined by gravity and momentum, burning their fuel at rates set by nuclear physics, shining with light produced in their cores and radiated into space. And the night is calm here in your room, where the only motion is your slow breathing and the gentle rise and fall of your chest, where the only sound might be the quiet settling of your house or the distant murmur of wind or traffic. All of it peaceful, all of it ordinary, all of it safe. Your breathing slows naturally without thought as your body remembers how to rest. Each inhale brings in air that has circled the planet countless times, shared by forests and oceans and every living thing, a communal atmosphere that connects all life on Earth. Each exhale releases it back, a small contribution to the atmosphere that wraps our planet in a protective layer, filtering harmful radiation from space, holding in heat, creating weather patterns, enabling the existence of liquid water and everything that depends on it. You are held by gravity, surrounded by air, resting on a planet that orbits a stable, middle-aged star in a quiet region of a spiral galaxy. That galaxy contains hundreds of billions of other stars, many with their own planets, and at its centre sits a supermassive black hole that has been there for billions of years, anchoring everything in place, influencing the motions of stars and gas across thousands of light years. And beyond our galaxy, there are hundreds of billions of other galaxies, each with their own stars and black holes and cosmic dramas, all of it unfolding slowly, patiently, across the vastness of space. But right now, all that vastness is somewhere else. Right now, you're here, in this small space, in this quiet moment. The universe is large enough that it doesn't need you to carry it or understand it, or even think about it. You can simply exist within it, a small point of awareness resting peacefully, while everything else continues on its way. Galaxies rotate, stars fuse hydrogen, black holes wait in silence, and none of it requires anything from you right now except perhaps a sense of wonder, and even that can wait until morning. Your thoughts can become light now, ungripped, free to drift wherever they want or nowhere at all. There's no need to hold on to any particular idea, no need to remember facts or sequences or explanations. All of that information will still be there tomorrow if you want it. The universe will still be full of black holes and stars and galaxies. The laws of physics will still operate the same way. Everything will wait for you, patient and unchanged. For now, you can let it all float away like leaves on a gentle stream, moving softly out of sight, leaving you in stillness. The room around you is still and safe, a small bubble of familiar space in the vast cosmos. The world outside is turning slowly beneath the stars, rotating once every 24 hours, a rhythm so steady we've used it to measure time for all of human history. The stars themselves appear to wheel across the sky, marking out the hours with ancient patient light. Photons that began their journey years or centuries ago and happen to arrive tonight, just in time to quietly illuminate the darkness. Nothing is rushing, nothing is demanding your attention. Even your body knows how to rest without your conscious guidance, how to breathe and circulate blood and repair cells while you drift in the soft space between waking and sleep. Your heart beats steadily, slowing as you relax, your muscles releasing their tension, your mind letting go of the day's concerns and tomorrow's plans. Everything can wait. Everything is exactly as it should be. Black holes, for all their strangeness and power, are just one more part of the universe's inventory, one more way matter and energy can arrange themselves according to physical law. They're remarkable, certainly worth studying and thinking about, but also understandable, governed by the same forces that govern everything else. They don't break the rules of physics. They follow them, even in the most extreme circumstances imaginable. And that's comforting in a deep way. It means the universe is consistent, predictable, knowable, even when it surprises us with phenomena we didn't expect. As you sink deeper into relaxation, your awareness of the room dims and softens. The details blur, the sharp edges of furniture and walls fading into gentle shadows. The boundaries between yourself and your surroundings become less distinct. You're still here, still breathing, still present, but in a quieter, gentler way. Thoughts rise and fall without urgency, like slow waves on a calm sea, each one rolling in, lingering briefly, then receding back into stillness. Nothing needs to be done. Nothing needs to be figured out. Everything can wait until morning, or even longer. The universe itself is a kind of vast, slow machine, running according to principles that are beautiful in their simplicity. Mass curves space-time, creating what we experience as gravity. Energy moves from hot regions to cold regions, creating flows and patterns. Light travels at a constant speed through vacuum, the ultimate speed limit of cause and effect. Entropy increases over time, giving direction to change. These rules have held for billions of years and will continue holding for billions more. They don't need our attention or approval. They simply are fundamental features of reality, and we exist within their framework, supported and shaped by them. In the grand scheme of things, you're very small. But small doesn't mean insignificant or unimportant. You're a part of this universe, made of the same atoms that make up stars and planets and black holes, governed by the same forces, participating in the same cosmic story. Your existence is woven into the fabric of everything, connected to distant galaxies by invisible threads of gravity and time and the shared history of matter itself. The atoms in your body were forged in stars that lived and died billions of years ago, scattered into space by supernova explosions, gathered into new clouds of gas, and eventually incorporated into the solar system and Earth and eventually you. Tonight that connection doesn't require effort. It's automatic, intrinsic, effortless. You're part of it all just by being here, breathing, resting, existing. The black holes will continue their patient wait in distant space, warping space-time around them, occasionally accreting a bit of gas or merging with another black hole across timescales of millions or billions of years. The stars will burn and shine, converting mass into energy through nuclear fusion, slowly working through their fuel supplies. Galaxies will turn, following orbits determined billions of years ago by the distribution of matter after the Big Bang. And you will sleep, held gently by the same physics that holds everything, drifting peacefully through the night until morning light finds you again, bringing with it a new day on this small, safe planet. Take a slow inhale if you'd like, bringing air deep into your lungs, feeling your chest expand and your diaphragm descend, and then release it in a longer exhale, letting everything soften and settle, muscles relaxing, mind quieting, thoughts becoming lighter and less defined. Let your eyes close if they haven't already, or simply let your gaze unfocus, looking at nothing in particular, allowing vision to soften into gentle darkness. The universe is here, vast and steady, and you are here within it, small and safe, resting in the knowledge that everything is exactly as it should be. Gravity holds you with the same reliable force it has exerted every moment of your life. Time flows forward at its usual pace, seconds becoming minutes, minutes becoming hours. The night surrounds you with its quiet, a temporary darkness that will give way to dawn, just as it has every day since Earth formed 4.5 billion years ago. And all of that will continue, gently and reliably, while you fall asleep, your awareness fading into dreams or peaceful blankness, your body and mind taking the rest they need. The next story is about to begin. Please relax and enjoy. Let's begin with something simple and quiet. Something vast but reassuringly slow. Volcanoes. They're Earth's patient way of letting go, of releasing heat that's been building for longer than any human timescale can comfortably hold. Think of them as the planet's slow-release valves, channels through which deep warmth travels upward, reshaping land grain by grain, flow by flow, across spans of time so long they make a human lifetime feel like a single breath. And here's the thing, you don't need to remember any of this. The facts can drift past you like warm air cooling in a quiet room. Let them settle where they will. A volcano, at its most basic, is simply an opening. It's a place where material from deep inside Earth can reach the surface. That's all, no drama required. Just geology doing what geology does, moving, shifting, releasing. When we talk about what's happening beneath our feet, we use a particular word for the melted rock that hasn't yet seen daylight: magma. It sits there in chambers and pockets, warm and patient, waiting for the conditions that might let it rise. And when that same material finally does emerge, when it flows out onto the surface where air and sky can touch it, we call it lava. Same substance, different location, different name. It's a small distinction, but it helps us talk about where things are in their journey from deep to shallow, from hidden to visible. Now, magma isn't just melted rock. It often contains dissolved gases, water vapor, carbon dioxide, sulfur compounds and others, held in solution by the enormous pressure of the rock above. Deep underground, that pressure is so great that gases stay dissolved, invisible, part of the liquid mixture. But as magma rises toward the surface, pressure decreases. Think of opening a bottle of carbonated water. The release of pressure lets carbon dioxide come out of solution, forming bubbles. The same principle applies here, though on a much grander scale and over much longer periods. As magma ascends through fractures and conduits in the crust, those dissolved gases begin to form bubbles, expanding as pressure continues to drop. This process matters quite a bit, because gas content and behavior influence how a volcano will eventually express itself at the surface, but we'll return to that later when we're ready. Volcanic activity is one of the ways Earth releases its internal heat. Our planet is warm inside, not metaphorically, but literally, measurably warm, and that heat comes from two main sources. Some of it is original heat, left over from Earth's formation 4.5 billion years ago, when countless collisions of smaller bodies released energy that melted and shaped the early planet. That primordial warmth is still radiating outward, slowly, steadily. The other source is radioactive decay, elements like uranium, thorium and potassium scattered throughout Earth's interior, break down over geological time, and that decay releases heat, continuously. Together, these processes keep the inside of our planet far warmer than the cold of space would otherwise allow, and volcanoes are one outlet through which that warmth finds its way to the surface. Volcanoes don't appear randomly across Earth's surface. They tend to form in specific geological settings, places where the conditions are just right for magma to form and rise. This isn't a matter of chance or cosmic whim. It's the result of plate tectonics, the slow dance of Earth's outer shell. We'll explore those settings in detail soon enough, but for now, just hold the idea that volcanoes have preferred locations, zones where the planet's internal machinery makes their existence not just possible but likely, even inevitable. When scientists talk about volcanoes, they often describe them as active, dormant, or extinct. These categories are based on recent behavior, though recent in geological terms can span thousands of years. An active volcano is one that has erupted, in recorded history or shows clear signs of ongoing unrest: gas emissions, seismic activity, ground deformation. A dormant volcano hasn't erupted recently but still has the potential to do so. It's sleeping, not dead. An extinct volcano is one that scientists believe is unlikely to erupt again, often because the geological conditions that created it have shifted or ceased. Of course, these distinctions aren't always sharp. Sometimes a volcano thought dormant surprises everyone. Earth keeps its secrets well, and our observations, however careful, cover only the thinnest slice of geological time. Let that foundation settle for a moment. We've established the basics: what a volcano is, what magma and lava are, why Earth is warm inside, why volcanoes form where they do rather than scattered randomly. Now we can move gently into the question of location, into the specific settings where volcanoes prefer to grow. Many volcanoes form along tectonic plate boundaries. Earth's outer shell, the lithosphere, is divided into several large plates and many smaller ones, all floating on the softer, slowly flowing rock of the mantle beneath. These plates move, not quickly by human standards, typically just a few centimeters per year, about the rate your fingernails grow, but over millions of years that motion reshapes continents, opens and closes ocean basins, builds mountains, and yes, creates volcanoes. Where plates interact, dramatic things can happen, albeit slowly. Convergent boundaries are places where two plates move toward each other. The specifics of what happens next depend on what kind of crust is involved. When an oceanic plate meets a continental plate, the denser oceanic plate typically sinks beneath the lighter continental plate in a process called subduction. Picture one massive slab of rock sliding beneath another, descending back into the mantle. As that oceanic plate descends, it carries with it water, locked in minerals, trapped in sediments, and that water becomes crucial. At depth, heat and pressure release the water, which then rises into the wedge of mantle above the subducting plate. Water lowers the melting point of rock. It allows the mantle to melt more easily than it would if dry, generating magma that can rise toward the surface. This is why chains of volcanoes so often form parallel to subduction zones. Think of the Cascade Range in the Pacific Northwest, or the volcanic arc of Japan, or the Andes along the western edge of South America. They're all expressions of this process. Long lines of potential and actual volcanic vents marching along the edge where one plate dives beneath another. The subduction process itself is worth lingering on, because it's one of the most important geological processes shaping our planet's surface. As the oceanic plate bends and descends into the mantle, it generates earthquakes, lots of them at varying depths. Shallow earthquakes occur where the plates first meet and begin to grind past each other. Deeper earthquakes happen as the slab continues its descent, sometimes reaching depths of several hundred kilometers before the slab becomes so warm and weak that it can no longer fracture in the brittle way that produces earthquakes. The descending slab also drags down sediments that have accumulated on the ocean floor, layers of mud, sand, organic material, all compressed and carried into the depths. Some of this sediment gets scraped off and piled up at the edge of the overriding plate, forming what's called an accretionary wedge. But some of it continues down with the slab, and eventually those sediments, along with the altered oceanic crust itself, begin to release fluids as they heat up. These fluids don't just contain water. They carry dissolved elements, sodium, potassium, silica, trace metals, and they migrate upward through the mantle wedge above the slab. The introduction of these fluids causes partial melting of the mantle rock. Not complete melting, the entire mantle doesn't turn to liquid, but enough that pockets and zones of magma begin to form. This magma is different from the magma that forms at mid-ocean ridges. It's been influenced by the fluids from the slab, enriched in certain elements, more evolved chemically. As this magma rises, it may stall in chambers within the crust, where it can sit for thousands of years, slowly crystallizing, changing composition as minerals settle out or as fresh magma is added from below. Eventually, some of this magma reaches the surface, erupting to build the volcanoes we see in subduction zone settings. Divergent boundaries, by contrast, are places where plates pull apart. As the plates separate, the pressure on the mantle beneath decreases. Lower pressure makes it easier for rock to melt, even without adding water, so magma can form and rise to fill the gap. This process creates new crust as the magma cools and solidifies. Much of this happens beneath the ocean, hidden from casual view. Mid-ocean ridges are the largest volcanic systems on Earth by length. Tens of thousands of kilometers of underwater mountain ranges where new oceanic crust is continuously being born. The rock there is mostly basalt, dark and fine-grained, formed from magma that cools relatively quickly in contact with cold seawater. Most people will never see these ridges directly, yet they represent the planet's most voluminous volcanic activity, a continuous, slow process of creation happening in the deep and the dark. The process at mid-ocean ridges is remarkably consistent, yet it varies in detail from place to place. Some ridges spread quickly, pulling apart at rates of 10 centimeters per year or more. Others spread slowly, just a centimeter or two per year. Fast-spreading ridges tend to have smooth, broad topography and steady magma supply. Slow-spreading ridges are more rugged, with deeper rift valleys and more episodic volcanic activity. But in all cases, the fundamental process is the same. Plates pull apart, mantle rises to fill the gap, pressure drops, melting occurs, magma ascends, and new crust forms. It's a factory for oceanic crust, operating continuously, building the floors of all the world's ocean basins. Not all volcanoes fit neatly at plate boundaries, though. Some form above what are called hotspots. persistent upwellings of unusually hot mantle material rising from deep within Earth, possibly from the boundary between the mantle and the core, though scientists continue to debate the precise mechanisms and depths involved. A hotspot stays relatively stationary while the tectonic plate above it moves. Magma generated by the hotspot punches through the plate, creating a volcano. As the plate continues its slow drift, that volcano eventually moves away from the heat source and becomes inactive, while a new volcano begins to form over the hotspot. Over millions of years, this process can create a chain of islands or seamounts, each one a snapshot of where the plate was at a particular moment in geological time. The Hawaiian Islands are the classic example, a string of volcanic islands tracing the movement of the Pacific plate over a deep mantle plume, with the Big Island currently sitting above the hotspot and still growing, while the older islands to the northwest are slowly eroding and sinking, their volcanic fires long extinguished. The Hawaiian chain extends far beyond the islands you might visit on vacation. If you trace the line of seamounts to the northwest, you find the Emperor Seamounts, underwater mountains that continue the chain for thousands of kilometers across the Pacific floor. These seamounts are the ancient remnants of the same hotspot activity, dating back tens of millions of years. The chain even has a bend in it, the Hawaiian Emperor Bend, where the direction of the seamount chain changes abruptly. This bend records a change in the direction of Pacific plate motion that occurred roughly 50 million years ago. The hotspot stayed in place, but the plate changed course, and the volcanic trail it left behind preserves that history. Hotspots aren't unique to Hawaii. Yellowstone sits above a hotspot beneath the North American plate, and the track of that hotspot can be traced southwest across Idaho, in a line of progressively older volcanic fields. Iceland sits atop a hotspot that coincides with the Mid-Atlantic Ridge, which is why Iceland exists at all. It's a place where both divergent plate boundary volcanism and hotspot volcanism work together, building the island faster than erosion can tear it down. The Galapagos Islands, Reunion Island in the Indian Ocean, the Azores, all are hotspot volcanoes, each one marking a plume of heat rising from deep in the mantle. Now that we have a sense of where volcanoes form, plate boundaries, both convergent and divergent, and hotspots scattered across the globe, we can relax into considering what shapes they take. Volcano shape isn't arbitrary. It depends on the properties of the lava involved and the style of eruption, both of which are ultimately controlled by magma composition and gas content. Shield volcanoes are broad, gently sloping structures that can stretch for many kilometers. Their slopes are so gradual that if you were standing on one, you might not immediately realize you were on a volcano at all. It could feel more like a long, gentle hill. Shield volcanoes form from repeated eruptions of low-viscosity lava, typically basaltic lava, which flows easily and spreads out in thin, far-reaching sheets before cooling. Each eruption adds another layer, and over time, often over hundreds of thousands or even millions of years, the accumulation of these flows builds a broad, dome-like mountain. The Hawaiian volcanoes are shields, and Mauna Loa, one of the most famous, is also one of the largest mountains on Earth by volume, though much of it is hidden beneath the ocean if you measure from its base on the seafloor to its summit. Mauna Loa rises more than 9 kilometers, taller than Mount Everest, though most of that height is underwater. The construction of a shield volcano is a patient process. Each lava flow might be only a meter or two thick, spreading out over several square kilometers before solidifying. Over time, hundreds or thousands of such flows stack up, each one contributing a thin layer to the edifice. The volcano grows slowly, imperceptibly from a human perspective, but steadily. Some shield volcanoes have summit calderas, large depressions at the top, formed when the summit collapses into a partially emptied magma chamber. The caldera can then become the site of future eruptions, with lava filling and refilling the depression over time. Stratovolcanoes, also called composite volcanoes, are steeper and more classically cone-shaped. They're built from many layers, strata, hence the name. These layers can include both lava flows and deposits of volcanic ash and other fragmented material. Stratovolcanoes tend to form where the magma is more viscous, often richer in silica, which doesn't flow as easily as basaltic lava. The result is steeper slopes, and a greater likelihood that eruptions will involve both flowing lava and explosive ejection of ash and rock. Many of the world's most visually striking volcanoes, Mount Fuji, Mount Rainier, Mount Vesuvius, are stratovolcanoes. They're symmetrical cones the result of countless eruptions layering material over geological time. The internal structure of a stratovolcano is complex. If you could slice one open and look at a cross-section, you'd see layers of lava flows interbedded with layers of ash, scoria, and other pyroclastic material. Some layers might be thin, representing small eruptions. Others might be thick, marking larger events. The volcano might have been built over hundreds of thousands of years, with long quiet periods between active phases. During those quiet times, erosion works to carve gullies and valleys into the flanks, only for the next eruption to fill them in again with fresh material. The competition between construction and erosion shapes the volcano's final form. Stratovolcanoes can also develop complex internal plumbing systems. Magma doesn't always rise straight up through a single central conduit. Sometimes it takes advantage of weaknesses in the rock, rising through networks of dikes and sills, sheet-like intrusions of magma that cut through or spread between existing rock layers. Some magma gets trapped in these intrusions and cools underground, never reaching the surface. Other magma finds pathways to flank vents, secondary openings partway up the volcano's slope. Over time, a stratovolcano can develop a whole system of vents, chambers, and conduits, making its behavior complex and sometimes difficult to predict. Cinder cones are smaller, simpler structures, often forming relatively quickly compared with the long construction timelines of shields and stratovolcanoes. A cinder cone builds when blobs of lava are ejected into the air during an eruption. As these fragments fly through the air, they cool and solidify before landing around the vent, piling up into a steep-sided cone of loose, fragmented rock called cinders or scoria. Cinder cones are often just a few hundred meters high and can form in a matter of months or years. They're sometimes found on the flanks of larger volcanoes, small satellite vents that opened during a particular eruptive episode. The eruptions that build cinder cones are called strombolian eruptions, named after Stromboli, a volcano in Italy that exhibits this style of activity almost continuously. The eruptions aren't usually dangerous at a distance. They're more like vigorous fountaining, with globs of molten rock arcing through the air and landing nearby. Up close, of course, being pelted with molten rock is hazardous, but from a few hundred meters away you can watch the show relatively safely. The fragments cool quickly in flight, forming a frothy, vesicle-rich rock that's full of gas bubbles. When these fragments land, they pile up loosely, building the cone. Because the material is unconsolidated, just piled up rather than welded together, cinder cones erode relatively quickly once activity stops. Rain and wind can tear them down in a few thousand years, which is fast by geological standards. Calderas are a different kind of feature altogether, not a mountain, but a depression. A caldera forms when a magma chamber beneath a volcano empties, either through a large eruption or through the magma draining away laterally. Without the support of the magma, the ground above collapses, creating a large, often circular or oval depression. Some calderas are many kilometers across. The collapse itself can be gradual or sudden, and the resulting landscape is often dramatic, a wide, relatively flat floor surrounded by steep walls. Over time, calderas can fill with water, forming lakes, or they can become the site of renewed volcanic activity if magma returns to the region. Crater Lake in Oregon occupies a caldera formed when Mount Mazama collapsed roughly 7,700 years ago. The caldera is not the result of an explosion blowing the top off the mountain, but rather the collapse following the evacuation of the magma chamber. It's a subtle but important distinction. Some calderas are associated with truly enormous eruptions. The Yellowstone caldera, for instance, formed during a massive eruption roughly 640,000 years ago that ejected more than 1,000 cubic kilometers of material. That's a volume difficult to grasp. Imagine a cube 10 kilometers on each side filled with ash and rock fragments. The eruption blanketed much of North America with ash, and the collapse created a caldera that's roughly 55 by 72 kilometers. Since then, smaller eruptions have partially filled the caldera with lava flows, and the ground continues to rise and fall as magma moves beneath the surface, though the likelihood of another super-eruption in any human-relevant time frame is extremely low. Many volcanoes have summit craters, circular or irregular depressions at the top, where volcanic vents release gases, lava, or both. These craters mark the point of most recent activity, though not all eruptions happen at the summit. Flank eruptions, where magma finds a pathway to the surface partway down the volcano's slope, are also common. The summit crater is often where you'll see fumaroles, vents releasing steam and volcanic gases, a reminder that even when a volcano isn't actively erupting, the heat beneath is still present, still working its slow way toward the surface. Some craters contain small lakes, fed by rain or snowmelt, and the water can be acidic from dissolved volcanic gases. Other craters are dry, dusty places, slowly filling with windblown debris between eruptions. With the shapes of volcanoes sketched out, we can ease into the personality of lava itself, how it behaves, how it moves, what determines whether it flows like a slow river or barely creeps along before freezing in place. The key property here is viscosity, which describes how easily a fluid flows. Honey has high viscosity, it pours slowly. Water has low viscosity, it pours quickly. Lava's viscosity depends on several factors, most notably temperature and composition. Hotter magma usually flows more easily than cooler magma. Heat keeps the atoms moving, prevents them from locking together into a solid structure. As lava cools, it stiffens, becomes more resistant to flow, until eventually it stops moving altogether and solidifies into rock. Composition matters too. Magma with more silica, silicon and oxygen, the building blocks of many minerals, tends to be more viscous. Silica forms long chains and networks of molecules that tangle together, making the liquid thicker, stickier, less willing to flow. Basaltic. Magma, relatively low in silica, flows easily when hot, spreading out in broad, thin sheets. Rhyolitic magma, rich in silica, is thick and sluggish, more likely to pile up near the vent than to flow far from its source. The temperature of erupting lava varies depending on composition. Basaltic lava can erupt at temperatures around 1200 degrees Celsius. That's hot enough to make the lava glow bright orange or yellow, hot enough that you can feel the radiant heat from meters away. Rhyolitic lava, by contrast, might erupt at only 800 to 1000 degrees Celsius, still incredibly hot by everyday standards, but cooler than basalt, and that lower temperature contributes to its higher viscosity. The cooler lava is more sluggish, more prone to forming domes and short, thick flows rather than the long, fluid flows typical of basalt. When low-viscosity lava flows and cools, it can form smooth, ropey textures on its surface, patterns that look almost like frozen waves or coiled rope. This is called pahoho, a Hawaiian word that has been adopted into geological vocabulary worldwide. Pahoho forms when the surface of the flow cools just enough to form a flexible skin, which then wrinkles and folds as the still liquid lava beneath continues to move. The result is a surface that's smooth and undulating, surprisingly beautiful in its quiet patterns. You can walk on cooled pahoho relatively easily. The surface is uneven, but it's not sharp and it's mostly solid. In some places, the ropey folds are so well preserved that they look fresh even thousands of years after the eruption. Other lava, even basaltic lava, cools into rough, jagged textures called ie, another Hawaiian term. Ie forms when the lava flow is slightly cooler or moving more slowly, so the surface breaks into sharp, clinkery fragments as the flow advances. Walking on Iea is difficult. The surface is uneven, unstable, full of sharp edges that can cut through boot leather if you're not careful. The fragments are angular and brittle, piled loosely on top of each other, and they shift underfoot. Both Pahoho and Ae can come from the same eruption, the same lava source. The difference lies in cooling rate and flow conditions. A lava flow might start as Pahoho near the vent where it's hottest and flowing most freely, then transition to Ae as it cools and slows farther downstream. Lava flows cool from the outside first. The surface in contact with air loses heat more quickly than the interior, forming a solid crust while the interior remains molten. This crust acts as insulation, slowing the rate at which the interior cools. Beneath that crust, lava can continue moving for hours, days, even weeks, quietly flowing inside a self-made tube or channel. Some of these lava tubes remain intact after the eruption ends, creating natural tunnels that can stretch for kilometers. You can walk through some of them, long dark passages with smooth walls where molten rock, once flowed, now cool and silent. The floor might be flat and smooth where the last of the lava drained away, or it might be littered with collapsed debris from the ceiling. Lava tubes can be surprisingly large. Some are big enough to drive a truck through, though most are more modest. requiring you to stoop or crawl in places. The formation of a lava tube begins with a channel, a depression or pathway where lava preferentially flows. As lava continues to move through this channel, the edges and top crust over, forming a roof. The lava inside remains insulated, hot, and mobile. As long as lava continues to be supplied from the vent, it flows through the tube, sometimes for weeks or months. When the eruption finally stops, the lava drains out of the tube, leaving behind an empty tunnel. Some tubes have skylights, places where the roof has collapsed, opening a window into the tube. Others remain completely intact, their presence only revealed by subtle depressions or lineations on the surface. Some lava flows develop natural channels, pathways carved or built up over time as repeated surges of lava follow the same route down the volcano's slope. These channels act like slow rivers of rock, directing the flow and allowing lava to travel farther than it otherwise might. The edges of the channel cool and solidify, forming levees that contain the flow, while the centre remains liquid and mobile. It's a strangely orderly process, this flowing of stone, governed by the same principles of fluid dynamics that shape water flowing in a stream. The main difference is timescale and temperature. Lava flows at meters per hour or per day, not meters per second, and it's hundreds of degrees hotter than boiling water. When lava cools completely, it becomes igneous rock. Igneous, from the Latin for fire, though the process is more about cooling than burning. The specific type of igneous rock depends on composition and cooling rate. Fast cooling produces fine-grained rock or even volcanic glass like obsidian if cooling is extremely rapid. Obsidian forms when lava cools so quickly that crystals don't have time to grow. The atoms freeze in place in a disordered, glassy structure. The result is a rock that's smooth, glassy, and can be incredibly sharp when fractured. Ancient peoples used obsidian to make cutting tools, arrowheads, and blades because a freshly broken edge can be sharper than steel. Slow cooling, which usually happens when magma solidifies underground rather than at the surface, allows crystals time to grow, producing coarse-grained rock like granite. The rock records the conditions of its formation, holding information about temperature, pressure, composition, cooling history. A quiet archive of geological processes written in mineral grains and textures. Now we shift from glowing rock to the fine, dusty side of volcanoes, ash and what it becomes over time. Volcanic ash is made of tiny fragments of rock, minerals and volcanic glass, shattered and ejected during explosive eruptions. Despite the name, it's not soft or fluffy like the ash left by burning wood. Volcanic ash is hard, abrasive, made of sharp-edged particles that can damage engines, clog filters, scratch surfaces. The particles range in size from fine dust, almost too small to see, to coarser grains like sand. When fresh, ash can be grey, black, brown, reddish, depending on the minerals involved and the degree of oxidation. The formation of volcanic ash is a violent process. During an explosive eruption, magma is torn apart by rapidly expanding gases. The fragmentation is so thorough that individual mineral grains are separated, glass is shattered into tiny shards, and rock is pulverized into dust. All of this material is hurled into the air, carried upward by the force of the eruption. The finest particles can be lifted tens of kilometers into the atmosphere, while larger fragments fall back to Earth more quickly. The ash cloud, if large enough, can block out the sun, turning day to twilight and covering the landscape in a grey mantle. Ash can be carried far from its source by wind. How far depends on particle size and the altitude the ash reaches. Fine ash, ejected high into the atmosphere by a powerful eruption, can drift for hundreds or even thousands of kilometers before settling. Larger particles fall closer to the source, often within hours or days. The pattern of ash deposition creates layers, distinct horizons in the geological record that can be traced across wide areas. These layers are useful to scientists. They act as time markers, allowing correlation of deposits and events across different locations. If you find the same ash layer in two widely separated areas, you know that those two locations were both affected by the same eruption, and you can use that to establish a relative timeline. Some ash falls into the ocean, where it settles to the seafloor and becomes part of the sediment record. Deep-sea cores drilled from research vessels sometimes contain multiple ash layers, each one recording a past eruption. By analysing the chemistry of the ash and comparing it to known volcanoes, scientists can sometimes identify which volcano produced which layer, building up a history of eruptions going back millions of years. Over time, volcanic ash weathers. Rain and chemical reactions break it down, releasing minerals into the soil. This is why many volcanic regions have fertile soils. The ash contains elements like potassium, phosphorus, calcium, magnesium, nutrients that plants need. As the ash weathers, these nutrients become available, replenishing the soil in ways that constant cropping or erosion might otherwise deplete. Many of the world's most productive agricultural regions are on volcanic soils. The slopes of volcanoes in Indonesia, Central America, Italy, the Pacific Northwest. It's a quiet exchange. The mountain gives ash, time and water turn ash to soil, and plants grow thick and green where once there was only rock and heat. The weathering of volcanic ash proceeds through several stages. Initially, the fresh ash is glassy and reactive, vulnerable to chemical attack by slightly acidic rainwater. The glass dissolves slowly, releasing ions into solution. These ions can precipitate as secondary minerals, clays, zeolites, iron oxides, which gradually replace the glass. Over thousands of years, the ash layer transforms from a loose deposit of sharp particles into a consolidated layer of clay-rich soil. The transformation is slow, but it's also thorough. Eventually, you might not recognize the soil as having been ash unless you know what to look for. Volcanic soils, once stable, can support dense plant growth. Forests reclaim the slopes, grasses cover the lowlands, crops flourish in the fields. The landscape settles into a long calm period, and the memory of fire fades, though the potential remains. Old ash layers, buried and compressed, can become part of the rock record. Geologists read these layers like pages in a book, reconstructing eruption histories, understanding the frequency and scale of past events, building a picture of how a particular volcano behaves over time, spans far longer than human observation can cover. In some places, volcanic ash has been buried and compressed to the point that it's become rock, a process called lithification. The resulting rock, called tuff, is often soft and easy to carve, which is why some ancient cultures used it for building material or carved dwellings directly into tough cliffs. The tuff from the eruption that created the Yellowstone caldera, for instance, can be found across much of the western United States, a layer of volcanic rock preserving the record of that enormous event. Volcanic deposits create new landforms too. Ash and lava can fill valleys, bury old surfaces, build plains where once there were hills. Over time, erosion reshapes these deposits, carving canyons, exposing colourful layers, creating badlands or plateaus. Even after the eruptions stop, the landscape continues to change, but the pace is slow, measured in centuries and millennia rather than days or years. In deep time, volcanic material becomes part of Earth's slow recycling, the endless process of creation and destruction, burial and exhumation, melting and solidifying that has shaped the planet's surface for billions of years. Now we glide outward to a quieter truth, one that surprises many people when they first encounter it. Most of Earth's volcanic activity happens where few people ever see it, deep beneath the ocean. The seafloor is volcanically active, and in fact, a large portion of all volcanic activity on our planet occurs underwater, hidden from view, unnoticed except by the scientists who study it. Mid-ocean ridges are the largest volcanic features on Earth by length. They form a continuous system of underwater mountain ranges stretching more than 60,000 kilometers through the world's ocean basins. At these ridges, tectonic plates pull apart, and magma rises from the mantle to fill the gap. As the magma cools, it solidifies into new oceanic crust, which then spreads away from the ridge as more magma rises behind it. This process, called seafloor spreading, has been creating new ocean floor for hundreds of millions of years. The ridges themselves are not smooth or uniform. They're rugged, fractured, cut by transform faults and rift valleys, dotted with volcanic cones and fissures. But they're also remote, deep, difficult to study directly. So much of what we know comes from sonar mapping, submersible dives, and seafloor drilling. The discovery of mid-ocean ridges and seafloor spreading revolutionized geology in the mid-20th century. Before then, scientists didn't understand how continents could move or how ocean basins formed. The mapping of the seafloor, particularly the discovery that it was youngest at the ridges and progressively older moving away from them, provided the key evidence for plate tectonics. It showed that the seafloor wasn't static but was being continuously created and destroyed, and that the ocean basins were relatively young features geologically speaking. The oldest seafloor is only about 200 million years old, ancient by human standards but young compared to continental rocks that can be billions of years old. When lava erupts underwater, it behaves differently than it does on land. The surrounding water is cold, near freezing in the deep ocean, and it cools the lava very rapidly. This rapid cooling can produce distinctive forms, particularly pillow lava. Pillow lava forms when the surface of a lava flow chills almost instantly upon contact with water, creating a glassy rind. The pressure of the still molten lava inside breaks through the rind, forming a new lobe that also chills rapidly, and the process repeats. The result is a pile of rounded, pillow-like shapes stacked and tumbled together, each one a snapshot of a moment when lava met water and froze. Pillow lavas are common along mid-ocean ridges and wherever underwater eruptions occur. Each pillow is typically a few tens of centimetres to a metre across, with a smooth, glassy outer skin and a more crystalline interior. If you cut one open, you can see radial cooling cracks and sometimes concentric layers that record the cooling history. Pillow lavas are so distinctive that geologists use them as an indicator of underwater eruption. When you find ancient pillow lavas now exposed on land, you know that those rocks formed beneath the sea and were later uplifted. Seamounts are underwater volcanic mountains. They rise from the ocean floor, sometimes reaching heights of several kilometres, though they don't break the surface. There are tens of thousands of seamounts scattered across the ocean basins, most of them extinct volcanoes, remnants of past activity. Some seamounts grow high enough to become islands. When a volcano builds from the seafloor and finally emerges above the waves, it becomes an island, a volcanic island, built entirely from erupted material. The Hawaiian Islands, Iceland, the Galapagos, the Azores, all are volcanic islands, mountains of lava and ash that happen to reach above sea level. Volcanic islands build slowly, through repeated eruptions over long periods of time. Each eruption adds material, raising the summit a little higher, expanding the island's footprint. Between eruptions, erosion works to tear the island down. Waves undercut the coasts, rain carves gullies, landslides strip away loose material. The balance between construction and destruction determines whether an island grows or shrinks. Young, active volcanic islands like the Big Island of Hawaii are still growing, their volcanoes adding new land faster than erosion can remove it. Older islands, no longer supplied with new lava, gradually erode away, sinking slowly as the seafloor beneath them cools and subsides. Eventually, millions of years after their volcanic fires go out, they may disappear beneath the waves entirely, becoming seamounts once more, completing a long geological cycle. The process of island subsidence is gradual but relentless. As new oceanic crust forms at a mid-ocean ridge, it's hot and buoyant, riding high. But as it moves away from the ridge, it cools, contracts, and becomes denser, causing the seafloor to sink. A volcanic island sitting on that seafloor sinks along with it. Over millions of years, an island can subside by hundreds or even thousands of meters. Some islands that once stood high above the waves are now flat-topped seamounts called guyots, their summits planed off by wave erosion when they were at sea level, then carried beneath the surface as the seafloor sank. Coral reefs can grow around volcanic islands, forming fringing reefs in shallow water near shore. As the island subsides, the reef continues to grow upward, keeping pace with the sinking land, and eventually the island can disappear entirely, leaving behind a ring of coral, an atoll. Charles Darwin proposed this mechanism for atoll formation in the 19th century, long before anyone had direct evidence for seafloor subsidence, and it turned out to be essentially correct. Drilling through atolls has confirmed that beneath the coral lies volcanic rock, the remnant of the island that once stood there. Hydrothermal vents often occur in volcanically active regions on the seafloor. These vents form where seawater seeps down through fractures in the crust, encounters hot rock or magma, becomes heated, and then rises back up, emerging as a jet of superheated, mineral-rich water. The temperature of the water can exceed 300 degrees Celsius, hot enough to melt lead, yet it doesn't boil because the pressure at depth is so great. When this hot water meets the cold ocean, dissolved minerals precipitate out, forming chimneys and mounds around the vent. Some of these structures, called black smokers, emit clouds of dark, mineral-laden water that look like smoke rising from a chimney. Others, white smokers, emit lighter-coloured fluids rich in different minerals. These vents support unique ecosystems, communities of bacteria, tube worms, clams, crabs, and other organisms that thrive in the heat and chemical richness, independent of sunlight, deriving energy from the chemicals in the vent fluids rather than from photosynthesis. It's a reminder that life finds a way, even in places that seem utterly inhospitable. The discovery of these vent communities in the late 1970s was a revelation. Before then, scientists assumed that all ecosystems ultimately depended on sunlight, that photosynthesis by plants or algae was the foundation of all food chains. But the vent communities proved otherwise. The bacteria at the base of these ecosystems use chemical energy from hydrogen sulfide and other compounds in the vent fluids, a process called chemosynthesis. The tube, worms, which can grow to lengths of more than a metre, have no digestive system. They host symbiotic bacteria in their tissues and rely entirely on the bacteria for nutrition. It's an alien world, in a sense, operating on completely different principles from the sunlit surface ecosystems we're familiar with. From the deep ocean, where volcanoes work in darkness and cold, we move into the quiet science of noticing them. How scientists monitor volcanoes, listening for changes, watching for signs of unrest, trying to understand what the volcano might do next. This work is patient, methodical, built on careful observation and the recognition of patterns over time. Seismometers are one of the primary tools for monitoring volcanoes. These sensitive instruments detect and record vibrations in the ground, including the small earthquakes that often accompany volcanic activity. When magma moves underground, it fractures rock, creating seismic signals. When fluids or gases flow through cracks and conduits, they can generate a kind of continuous tremor. By placing seismometers around a volcano and recording the earthquakes they detect, scientists can begin to understand where magma is moving, how fast it's rising, whether the activity is increasing or decreasing. Not every earthquake means an eruption is imminent. Volcanoes experience earthquakes all the time, and most of them lead nowhere. But changes in the pattern, frequency, or depth of earthquakes can be significant. It's about context, about seeing shifts in the baseline. Modern seismometers are remarkably sensitive. They can detect ground motions smaller than the width of an atom, vibrations that would be completely imperceptible to a person standing next to the instrument. This sensitivity allows them to pick up the faint signals of magma moving several kilometers beneath the surface, or the subtle tremor associated with gas escaping through fractures. By analysing the seismic waves, their frequency, amplitude, and arrival times at different stations, scientists can locate the source of the activity and sometimes infer what kind of process is producing it. Scientists also measure ground deformation, tiny swelling or sinking of the volcano's surface. When magma accumulates in a chamber beneath a volcano, it takes up space, and that can cause the ground above to bulge upward, sometimes by just a few centimeters, sometimes by meters, depending on the volume of magma and the depth of the chamber. When magma drains away or an eruption relieves pressure, the ground can subside. These movements are often too small and too slow to notice without instruments, but they're measurable. GPS stations placed around a volcano can detect changes in position with millimeter precision, tracking the slow inflation and deflation of the volcanic edifice. Satellite radar can map ground movement across wide areas, using a technique called interferometry that compares radar images taken at different times. The result is a detailed picture of how the surface is deforming, which in turn tells scientists something about what's happening below. Interferometric synthetic aperture radar, or INSAR, has become an invaluable tool for volcano monitoring. A satellite passes over a volcano repeatedly, sending down radar pulses and recording the reflections. By comparing the phase of the radar waves in images taken weeks or months apart, scientists can detect ground movements of just a few millimeters. The technique works even in remote areas, even through clouds, and it can cover entire volcanic regions in a single image. The data appears as colourful interference patterns called interferograms, where each colour cycle represents a certain amount of ground movement. Interpreting these patterns requires care, but they provide a synoptic view that would be impossible to achieve with ground-based instruments alone. Volcanoes release gases, water vapour, carbon dioxide, sulfur dioxide, hydrogen sulfide, and others, and the composition and quantity of these gases can provide clues about magma depth and movement. As magma rises, pressure decreases, and gases come out of solution, rising ahead of the magma itself. An increase in sulfur dioxide emissions, for instance, might suggest that fresh magma is approaching the surface. Scientists collect gas samples directly from fumaroles and measure gas concentrations in the air downwind from the volcano. Some monitoring stations use spectrometers to measure gases remotely, even from aircraft or satellites, tracking how emissions change over time. Gas monitoring isn't a perfect predictor. Gases can migrate through complex fracture networks, and the relationship between gas release and eruption isn't always straightforward, but it's another piece of the puzzle, another line of evidence. Different gases provide different information. Water vapor is the most abundant volcanic gas, but it's also ubiquitous in the atmosphere, so it's hard to use as a monitoring tool. Carbon dioxide is less abundant in air, and it can escape from deeper in the volcanic system than other gases, so changes in CO2 emissions can sometimes signal deep magma movement before other indicators appear. Sulfur dioxide is particularly useful because it's relatively rare in the atmosphere, and it's released in large quantities when magma degasses. Satellite instruments can measure sulfur dioxide plumes from space, tracking how much gas a volcano is releasing even if there's no access to the summit. Thermal sensors detect warming near vents and fissures. Increased heat flow can indicate rising magma or increased circulation of hot fluids. Infrared cameras, either ground-based or mounted on aircraft and satellites, can map temperature variations across a volcano's surface. A new hotspot, or a gradual warming of a crater floor, might signal changing conditions below. Thermal monitoring is especially useful for volcanoes that are difficult to access on foot, or for tracking changes over large areas. Many regions with active volcanoes have dedicated volcano observatories, institutions where scientists work full-time to monitor and study the local volcanoes. These observatories maintain networks of instruments, collect and analyze data, assess hazards, and provide information to emergency managers and the public. The work is long-term, often spanning decades. Volcanic unrest can last for months or years without leading to an eruption, and understanding what's normal for a particular volcano requires years of baseline data. Monitoring is about pattern recognition, about detecting the subtle shifts that might indicate an approaching eruption, and about being patient enough to watch and wait even when nothing dramatic is happening. The Hawaiian Volcano Observatory, established in 1912, is one of the oldest continuously operating volcano observatories in the world. For more than a century, scientists there have been monitoring Kilauea and Mauna Loa, building up an unparalleled record of volcanic activity. That long baseline allows them to understand the nuances of how these volcanoes behave, to recognize the early signs of an eruption, and to provide timely warnings. Other observatories around the world, in Japan, Italy, Indonesia, the Philippines, Alaska, and elsewhere, perform similar work, each one tailored to the specific volcanoes in their region. With that calm, attentive framework of monitoring in place, we can gently explore eruption styles, the range of behaviours a volcano might display when it does become active. There's no need to focus on fear or destruction here, just the physical processes, the ways in which magma, gas, and rock interact to produce different kinds of eruptions. Some eruptions are slow lava effusions rather than explosive events. Lava simply flows out of a vent or fissure, spreading across the ground, cooling as it goes. These effusive eruptions are common with low-viscosity basaltic magma and can continue for weeks, months, even years. The lava doesn't shoot into the air, it oozes, creeps, advances at a pace you could walk away from. It might destroy structures in its path by burying them, but it rarely poses a direct threat to human life because it moves slowly enough for people to evacuate. The 2018 eruption of Kilauea in Hawaii was largely effusive. Lava erupted from fissures in the Lower East Rift Zone, sending flows downslope toward the ocean. The flows were spectacular. Rivers of molten rock glowing orange in the darkness, advancing across roads and through forests, entering the sea in great clouds of steam. But they moved slowly, typically just hundreds of meters per day, giving people time to leave. The eruption lasted for months, eventually covering more than 30 square kilometers with new lava and destroying hundreds of homes. Yet the loss of life was minimal because the advance of the lava was predictable and slow. Eruption style depends partly on viscosity and gas content. High viscosity magma doesn't flow easily, and if it contains a lot of dissolved gas, pressure can build until the magma fragments explosively, shattering into ash and rock. This is how explosive eruptions happen. The gas expands rapidly as pressure drops, tearing the magma apart and propelling fragments into the air. The violence of the explosion depends on how much gas is present, how viscous the magma is, and how quickly the pressure is released. Some explosive eruptions are relatively modest, sending ash and rock a few hundred meters into the air. Others are far more powerful, creating eruption columns that reach tens of kilometers into the stratosphere. Water interacting with hot magma can create steam-driven eruptions, also called phreatic eruptions. If groundwater or surface water comes into contact with magma or very hot rock, it can flash to steam almost instantaneously. The rapid expansion of water turning to steam is incredibly energetic, and it can fragment rock and eject material even if no fresh magma is involved. These eruptions tend to be sudden and difficult to predict because they depend on water availability and subsurface conditions that can change quickly. Phreatic eruptions are often the first sign of renewed volcanic activity. As magma rises beneath a volcano, it heats the surrounding rock and any groundwater present. The heated water can boil and flash to steam, causing small explosions that eject old rock from the vent. These explosions can create craters and eject debris, but they don't involve fresh magma. If magma continues to rise and eventually reaches the surface, the eruption can transition from phreatic to magmatic, with molten rock joining the ash and steam. A volcanic plume is a rising column of ash, gas, and sometimes larger rock fragments ejected during an eruption. The plume rises because it's hot and less dense than the surrounding air. As it rises, it cools, and eventually it reaches a height where it's no longer buoyant. At that point, the plume spreads laterally, forming a mushroom-shaped cloud. Plumes vary widely in size and duration. Some are modest, rising just a few kilometers and lasting minutes or hours. Others are enormous, sustained for hours or days, reaching well into the stratosphere. The height a plume reaches affects how far ash can travel. Higher plumes inject ash into upper-level winds that can carry it around the globe. The 1991 eruption of Mount Pinatubo in the Philippines produced one of the largest volcanic plumes of the 20th century. The eruption column reached more than 35 kilometers into the atmosphere, well into the stratosphere. The ash and aerosols spread around the world, reflecting sunlight and causing measurable global cooling for several years. The eruption itself was powerful, but because scientists had successfully predicted it and evacuated tens of thousands of people from the area, the loss of life was relatively limited. It was a triumph for volcano monitoring and hazard communication. Volcanic lightning can occur within an eruption plume. As ash particles collide with each other during the explosive ejection, they can build up electrical charge through friction. When the charge difference becomes large enough, it discharges as lightning. The result is dramatic. Bright flashes and arcs of electricity within the dark ash cloud, lighting it from within. It's a phenomenon that photographers love, but it's just physics, the same process that creates lightning in a thunderstorm, playing out in the chaotic environment of an eruption column. The lightning can occur within the plume, between the plume and the ground, or even between different parts of the plume as charge separates. The ash particles act like the ice crystals in a thunderstorm, colliding and transferring charge until the electrical potential is large enough to overcome the resistance of the air. The discharges can be frequent during vigorous eruptions, creating almost continuous lightning within the ash cloud. Lava domes form when thick, viscous lava piles up near a vent rather than flowing away. The lava is too stiff to spread, so it mounds up, growing slowly as more lava is extruded from below. Domes can grow for months or years, adding material little by little. The outer surface cools and solidifies, but the interior remains hot and somewhat mobile. As the dome grows, the solid carapace can fracture and shed blocks of rock, or the dome can partially collapse, sending avalanches of hot rock and ash down the volcano's slopes. Despite the potential for sudden collapses, dome growth itself is usually a slow process, one that can be monitored and studied over time. The dome growing at Mount St. Helens after the 2004 eruption provides a good example. The dome grew slowly and episodically, with periods of active growth separated by pauses. At times, fresh lava would push up through the centre of the dome, tilting and fracturing the older, cooler rock. At other times, the dome would simply sit there, steaming and cooling. Scientists were able to monitor the growth closely, measuring the deformation, tracking the seismicity, and assessing the hazards. The growth continued for several years, eventually building a dome hundreds of meters high within the crater left by the catastrophic 1980 eruption. Even energetic eruptions follow consistent physical rules. The explosions, the ash clouds, the flows of lava, all of these are expressions of thermodynamics, fluid dynamics, material properties. There's no mystery here, no supernatural force, just heat, pressure, chemistry, and the behavior of matter under extreme conditions. Understanding these rules allows scientists to make sense of what they observe, to compare different eruptions, to develop models that can, in some cases, help predict future behavior. Now we zoom out to the planetary scale, considering how volcanoes fit into Earth's long, steady cycles, how they're part of the larger system that keeps our planet geologically active, that recycles crust and mantle, that shapes landscapes and influences climate over deep time. Volcanism is intimately linked to plate tectonics, the slow movement of Earth's lithospheric plates. Plate motion is driven by mantle convection, the gradual flow of warm, slowly deforming rock in the mantle. Hot material rises, cooler material sinks, and this circulation operating over millions of years drags the plates along. At convergent boundaries, where plates collide, one plate descends into the mantle in subduction zones. This process recycles oceanic crust back into the mantle, taking with it sediments, water, and altered minerals. Eventually, much of that material will be melted and brought back to the surface through volcanic eruptions, completing a cycle that can take hundreds of millions of years. The recycling is not perfect or complete. Some material gets carried deep into the mantle and may remain there for a very long time before being incorporated into rising plumes or mantle currents. Other material is returned to the surface relatively quickly. The system is complex with multiple pathways and timescales, but the overall result is that material circulates between the surface and the deep interior, mixing and being transformed along the way. Volcanoes are one surface expression of this deep recycling. They bring material from the mantle to the crust, releasing heat, building new land, contributing gases to the atmosphere. Over Earth's history, volcanism has played a significant role in shaping the atmosphere. Early in Earth's history, volcanic outgassing likely contributed much of the water vapour, carbon dioxide, nitrogen, and other gases that formed the early atmosphere. Over time, these gases helped create conditions suitable for liquid water and eventually for life. Even today, volcanoes release gases that become part of the atmospheric mix, though in much smaller quantities compared to the planet's early days. The early Earth was a very different place. The atmosphere was likely dominated by carbon dioxide and water vapour, with little or no free oxygen. Volcanic outgassing was intense, as the young planet was much more geologically active than it is today. Over billions of years, the carbon dioxide was gradually sequestered in rocks through weathering and precipitation of carbonate minerals, and oxygen levels rose as photosynthetic organisms evolved and spread. The atmosphere we have now, rich in nitrogen and oxygen, with only trace amounts of carbon dioxide, is the result of billions of years of geological and biological processes working together. Volcanic rocks create new crust when they cool and solidify. At mid-ocean ridges, basaltic lava forms the ocean floor, adding new crust at a rate of a few centimeters per year along each side of the ridge. On land, volcanic eruptions can build islands, thicken continental crust, create plateaus. The Deccan traps in India, the Siberian traps in Russia, the Columbia River basalts in the Pacific Northwest. These are examples of flood basalts, enormous outpourings of lava that covered vast areas, in some cases millions of square kilometers, with layer upon layer of solidified lava. These events occurred over geologically brief periods, typically a few million years, and they represent some of the largest volcanic events in Earth's history. The Siberian Traps eruption, which occurred roughly 250 million years ago, coincided with the Permian-Triassic mass extinction, the most severe extinction event in Earth's history. More than 90% of marine species and 70% of terrestrial vertebrate species went extinct. The exact causal mechanisms are still debated, but it's likely that the massive release of volcanic gases, carbon dioxide, sulfur dioxide, and others, triggered severe climate changes and ocean acidification. The eruption lasted for perhaps 1 million years or more, releasing enough lava to cover an area the size of Europe with layers of basalt kilometers thick. It's a reminder that volcanic eruptions, while usually local or regional phenomena, can sometimes have global consequences. Some volcanic aerosols, tiny particles and droplets, can reach high into the atmosphere and reflect sunlight, temporarily cooling Earth's surface. When a volcano injects large amounts of sulfur dioxide into the stratosphere, the gas reacts with water vapour to form sulfate aerosol particles. These particles are reflective and can remain aloft for months, or even a few years before settling out. During that time, they scatter incoming sunlight, reducing the amount of solar radiation that reaches the surface. The effect is measurable. Large eruptions in the past have caused temporary global cooling of a degree or more. But the particles eventually settle, the air clears, and temperatures return to their previous levels. It's a temporary perturbation, not a permanent change, though it can have significant short-term effects on weather and climate. The 1815 eruption of Mount Tambora in Indonesia was one of the most powerful eruptions in recorded history. It injected massive amounts of sulfur dioxide into the stratosphere, and the resulting aerosol clouds circled the globe. The year 1816 became known as the Year Without a Summer in parts of Europe and North America. Temperatures dropped, crops failed, and there were widespread food shortages. The cooling lasted for several years before the aerosol settled out and normal conditions returned. It's a sobering example of how a single volcanic eruption, however distant, can affect people on the other side of the world. Over geological time, Earth's surface changes gradually through countless small steps. Mountains rise and erode, continents drift, ocean basins open and close. Volcanoes are part of this ongoing transformation, adding material here, releasing heat, there, reshaping the land in episodes separated by long intervals of quiet. Earth stays dynamically active, constantly adjusting, constantly in motion, without any need to hurry. The pace is set by the slow convection of the mantle, by the steady decay of radioactive elements, by processes that operate on timescales so long they make human history seem vanishingly brief. And now we return to the bedside scale, to the quiet room, to the stillness of the night. We've travelled from the deep mantle to the ocean floor, from lava tubes to eruption plumes, from monitoring instruments to planetary cycles. Now we bring it all back to something simple and immediate. The ground beneath you, the warmth deep below, the patient work of a planet that never truly sleeps but never rushes either. Most nights the ground beneath you feels completely still. You lie in bed and there's no sense of motion, no vibration, no sign of the immense forces at work far below, and yet beneath the crust, heat moves slowly through solid rock. It doesn't race or surge. It diffuses, spreading outward at a pace determined by the thermal properties of the rock. This is conduction, the slow transfer of heat from warmer regions to cooler ones, atom by atom, grain by grain. It's so gradual that you could watch for a lifetime and never see a change, yet over millions of years, it reshapes the planet. Mantle convection is the long-term flow of warm material deep inside Earth. The rock in the mantle is solid, not liquid, but at the temperatures and pressures found there, over geological time, it behaves like a very slow fluid. Warmer rock rises, cooler rock sinks, and the circulation continues, driven by the heat coming from the core and from radioactive decay in the mantle itself. This convection is what drives plate tectonics, what causes the slow drift of continents, what brings magma to the surface at mid-ocean ridges and subduction zones. It's the engine beneath everything we've been discussing, and it operates on a timescale so vast that it's almost impossible to truly comprehend. The mantle convects at a rate of perhaps a few centimetres per year, similar to the rate plates move, because the two are linked. Over millions of years, that slow circulation has mixed the mantle, redistributed heat, controlled the planet's thermal evolution. Volcanoes are one way Earth releases heat without constant surface disturbance. Instead of the entire surface being molten, instead of heat escaping everywhere at once, it's concentrated at specific points, plate boundaries, hotspots, rifts. This allows much of the surface to remain cool, solid, stable, while heat is efficiently vented through these relatively narrow channels. It's an elegant system, a balance between the need to lose heat and the need to maintain a solid surface capable of supporting complex geology oceans, atmospheres, life. Many volcanic landscapes, after the eruption's end, become peaceful places. Forests grow back. Rivers return to their old courses or carve new ones through the fresh rock. Animals recolonize. The evidence of past violence, the ash, the lava flows, becomes substrate for new ecosystems. Lava becomes rock, hard and dark, providing raw material for soil formation. Rock weathers under the patient assault of water, air and living organisms, breaking down into minerals and particles. Those particles mix with organic matter, leaves, roots, fungi, bacteria, and become soil. Soil supports plants, plants support animals, and the landscape transforms from barren volcanic wasteland to thriving ecosystem. The timescale varies. Sometimes it takes decades, sometimes centuries, but the pattern repeats across volcanic regions worldwide. Life is resilient, opportunistic, good at finding footholds in the most unlikely places. Geological time is vast, vaster than most people ever pause to consider. 1 million years is a comprehensible number, but it's incomprehensible as a duration. It's long enough for mountains to rise and erode away, for species to evolve and go extinct, for continents to drift thousands of kilometers. And Earth's history encompasses not 1 million years, but 4.5 billion. 4,500 million years, a span so long that the entire history of human civilization, all of recorded history, all of the rise of agriculture and cities and technology, is a blink at the very end. Against that backdrop, most geological change feels gentle and gradual. There are sudden events, to be sure, earthquakes, volcanic eruptions, asteroid impacts, but even these are brief punctuations in a much longer, slower narrative. The dominant mode is patience. Tonight, you can borrow that patience. You can let your thoughts cool and settle like lava solidifying into stone. There's no need to hold on to anything, no need to worry or plan or remember. The facts about volcanoes, the mechanisms of eruption, the slow dance of plates, they've passed through your awareness, and whether you recall them tomorrow or not doesn't matter. They're part of the planet's story, not yours to carry. You can set them down and let them rest. Earth continues its quiet heat cycle. Deep below, radioactive elements decay, releasing warmth. The core remains molten, convecting slowly, generating the magnetic field that shields the planet from solar radiation. The mantle circulates, rising here, sinking there, moving plates, building mountains, creating volcanoes. The surface receives sunlight, radiates heat back to space, weathers and erodes, shifts and changes. It's a system in dynamic balance, not static but stable, capable of sustaining itself over billions of years. And you, right now, in this moment, are resting on the surface of that system, safe, supported, part of the same planet that builds volcanoes and recycles crust, and releases heat through vents and fissures scattered across the globe. The planet is doing its long work, the work of geology, the work of deep time. It doesn't need your help or your attention. It will continue regardless, patient and inexorable. And you're allowed to do the simplest work of all, the work of resting, of breathing, of letting your body and mind settle into the quiet that the night offers. The ground beneath you is still, the air around you is calm. The distant fires of Earth's interior are banked and slow, working their way upward grain by grain, century by century, asking nothing of you. You can close your eyes and let the weight of your body sink into the bed, trusting that the surface will hold you, that the crust beneath is solid, that the cycles of heat and rock and time will carry on without you needing to tend them. Sleep is its own kind of geology, a slow process, a settling, a release of the day's accumulated tension. Like lava cooling into stone, your thoughts can slow and solidify, your awareness can dim and fade, until you drift into the dark and quiet space where rest lives. The planet turns, the mantle convects, the heat rises, the crust holds, and you, safe in the stillness of the night, can let go and sleep. The next story is about to begin. Please relax and enjoy. Rain is liquid water falling from clouds to the ground. It's one of the most familiar things in nature, and yet when you pause to think about it, even this simple phenomenon is full of quiet complexity. Rain is part of the water cycle, that constant movement of water around Earth, from ocean to sky, from sky to land, and back again in loops that have been running for billions of years. Every raindrop you see has been somewhere else before. It has cycled through rivers, oceans, soil, plants, clouds, and now it falls again, repeating an ancient pattern that connects everything on the planet in a web of moisture and motion. Rain begins with water vapor, which is invisible. You can't see it in the air around you, even though it's there, mixed in with nitrogen and oxygen and all the other gases that make up our atmosphere. Water vapor is just water in its gaseous form, molecules moving freely, bouncing around, unattached to one another. It forms when liquid water evaporates, when the sun warms the ocean, or when moisture lifts from a lake, or when a wet street dries after a storm. The energy from heat allows water molecules to break free from the liquid and drift into the air as vapor. This vapor is light, it rises, it spreads, and it waits. The waiting is important in its way. Water vapor can linger in the atmosphere for days or even weeks, traveling with the wind, mixing with other air masses, moving across continents and oceans. During this time, the vapor is just one component of the air, invisible and unremarkable to anyone breathing it. But it carries with it the potential for rain, stored energy in the form of latent heat, moisture that will eventually return to the surface in one form or another. The atmosphere holds an enormous amount of water at any given moment. If all of it condensed and fell at once, it would cover the Earth's surface with about an inch of water. But it doesn't fall all at once. It falls gradually in specific places when conditions are right. The next step happens when air cools enough. Water vapor becomes droplets when air reaches a temperature where it can no longer hold all that invisible moisture. This temperature is called the dew point. Cooling to the dew point allows condensation to happen. Condensation is the opposite of evaporation. It's when water vapor turns back into liquid. But here's something interesting. Condensation doesn't usually happen all by itself, even when the air is cool enough. The vapor needs a little help. It needs something to gather on, something to give it a starting point. That's where condensation nuclei come in. Condensation usually needs tiny particles called condensation nuclei, and these particles are everywhere. They can be dust, sea salt, smoke, or pollen. They can be microscopic fragments of soil kicked up by wind, or tiny crystals of salt left behind when ocean spray evaporates, or particles released by factories and cars, or even bits of organic material from trees and plants. These nuclei are so small you'd never notice them, but they're floating all around you, thousands and thousands of them in every breath of air. When water vapor encounters one of these particles and the air is cool enough, the vapor begins to stick to it. A droplet starts to form, molecule by molecule, building up around the nucleus like a tiny shell of liquid. The process of a droplet forming on a nucleus is surprisingly delicate. The nucleus provides a surface, a place where water molecules can gather more easily than they could in empty air. Without the nucleus, water molecules would have to spontaneously cluster together, which requires much more cooling. Air would have to be supersaturated, cooled well below the dew point before droplets would form. But with nuclei present, condensation can happen right at the dew point, or even slightly before. The nucleus acts like a seed, a foundation on which the droplet can grow. Different types of nuclei work with different levels of efficiency. Sea salt particles are particularly good at attracting water. Because salt is hygroscopic, it absorbs moisture readily. Some particles are less effective, but even a speck of dust can work if the air is cool and moist enough. Cloud droplets start extremely small. We're talking about droplets that are only 10 or 20 micrometers across, far smaller than the period at the end of this sentence. They're so light that they can float in the air, held aloft by even the gentlest upward motion in the atmosphere. A cloud is really just a collection of billions of these droplets, all suspended together, drifting and shifting. From the ground, a cloud looks solid, but if you could walk through one, you'd just feel a cool mist. Each droplet is separate, floating in space, too small and too light to fall. When you see a cloud, you're seeing the collective effect of countless tiny droplets scattering sunlight. Each droplet acts like a tiny lens or mirror, bouncing light in different directions. White clouds are white because they scatter all wavelengths of visible light roughly equally. Darker clouds appear dark because they're thick enough that light can't penetrate all the way through them. The base of the cloud is in shadow. But whether a cloud is white, grey or nearly black, the droplets inside it are all transparent. The colour is an optical effect, a result of light interacting with vast numbers of droplets. But many droplets must grow before they can fall as rain. The challenge is that these tiny cloud droplets are in a kind of equilibrium. They're small enough that they don't fall, but they're also not growing much just by sitting there. For rain to happen, droplets need to get much bigger, hundreds of times bigger. They need to become heavy enough that gravity can pull them down through the air, even against the upward currents and the drag of the atmosphere. Rain happens when droplets become heavy enough to overcome rising air and drag, and there are a few different ways this growth can happen depending on the type of cloud and the conditions inside it. One common way droplets grow is by colliding and merging. This is called collision coalescence. Imagine millions of tiny droplets all drifting around inside a cloud. Some are moving up, carried by rising air. Some are starting to fall because they're slightly bigger. As they move, they bump into each other. When two droplets collide, they can merge into one larger droplet. That larger droplet is now a bit heavier, so it falls a little faster, and as it falls, it collides with even more droplets on the way down. Each collision adds more water, and the droplet grows. In warm clouds where the temperature is above freezing all the way through, this process can make raindrops efficiently. The droplets don't need to freeze. They just keep colliding and growing until they're big enough to fall all the way to the ground. The efficiency of collision coalescence depends on several factors. Droplet size is important. If all the droplets are exactly the same size, they'll all fall at the same speed, and they won't collide as often. But in real clouds, there's always a range of droplet sizes, and this creates different fall speeds, which creates more collisions. The strength of the updraft matters too. Strong updrafts keep droplets suspended longer, giving them more time to collide and grow before they fall out of the cloud. The concentration of droplets also plays a role. More droplets mean more potential collisions. In maritime clouds over the ocean, where condensation nuclei are less abundant and droplets tend to be larger on average, collision coalescence can produce rain quite quickly. In continental clouds over land, where there are more nuclei and droplets tend to be smaller, the process can take longer. In colder clouds, ice can help form precipitation too. When temperatures inside a cloud drop below freezing, ice crystals can start to form. These crystals are different from liquid droplets. They have a different structure, and they interact with water vapor in a special way. Ice crystals can grow by collecting water vapor directly from the air around them. Water vapor molecules can stick to the surface of an ice crystal and freeze onto it, adding layer after layer. This is called vapor deposition, and it can make ice crystals grow much faster than liquid droplets can grow by condensation alone. The reason ice crystals grow so efficiently has to do with a subtle difference in saturation. At the same temperature below freezing, the saturation vapor pressure over ice is slightly lower than the saturation vapor pressure over liquid water. This means that in a cloud containing both ice crystals and supercooled water droplets that are still liquid even though they're below freezing, the air can be saturated with respect to the water droplets but supersaturated with respect to the ice crystals. In this situation, water vapor will preferentially deposit onto the ice crystals and the crystals will grow rapidly. Meanwhile, the supercooled droplets might actually evaporate slightly to maintain equilibrium. This process, called the Bergeron process or the ice crystal process, is very important for precipitation formation in clouds that extend up into freezing temperatures. Ice crystals can also collide with droplets and other crystals. When an ice crystal bumps into a supercooled droplet, a droplet that's still liquid even though it's colder than freezing, the droplet can freeze onto the crystal instantly. This process, called riming, can make the crystal heavier and more complex in shape. Rimed crystals can look like small pellets of ice, completely coated in frozen droplets. Crystals can also collide with each other and stick together, forming larger clumps of ice called aggregates. Snowflakes are often aggregates, clusters of many individual ice crystals that have joined together during their fall. All of these processes help ice particles grow inside cold clouds, and when they get heavy enough, they start to fall. When ice falls into warmer air, it can melt into raindrops. As an ice crystal or snowflake falls from the cold upper parts of a cloud into the warmer air below, it begins to melt. The ice turns back into liquid water, and what reaches the ground is rain, not snow. This is actually how a lot of rain forms, even in the summer. The precipitation starts as ice high up in the cloud, then melts on the way down. So even on a warm day, the rain that falls on you may have been frozen just a few minutes earlier, thousands of feet above your head. The melting level, or freezing level, is an important boundary in the atmosphere. It's the altitude where the temperature is 0 degrees Celsius. Above this level, precipitation is likely to be frozen. Below it, precipitation is likely to be liquid. In winter, the freezing level can be quite low, sometimes even at ground level, which is when you get snow instead of rain. In summer, the freezing level is much higher, often several kilometers up, so precipitation melts long before it reaches the surface. Weather forecasters pay close attention to the height of the freezing level because it determines what type of precipitation will fall. Rain can fall from clouds that look dark or clouds that look gentle and grey. The colour of a cloud doesn't always tell you whether it's raining. A thick, dark cloud is often dark because it's very deep and blocks a lot of sunlight, and deep clouds often produce rain because there's more space for droplets to grow. But even a thin grey cloud can produce drizzle if the conditions are right. The darkness is about thickness and light, not always about rain itself. Rain often begins high above you and finishes its fall near the ground. The journey of a raindrop from cloud to earth can take minutes, depending on how high the cloud is and how big the drop is. During that fall, the drop is moving through different layers of air, each with its own temperature, humidity and wind. The drop might shrink a bit if it's falling through dry air and some of it evaporates. It might grow a bit if it's falling through a humid layer and collecting more moisture. It's a dynamic process, and every raindrop's journey is slightly different. A raindrop falling from a typical cumulus cloud might travel 2 or 3 kilometers before hitting the ground. If it's a small drop, falling at perhaps 2 meters per second, that journey could take 15 or 20 minutes. A larger drop, falling at 7 or 8 meters per second, might make the trip in just a few minutes. During that time, the drop is subject to all sorts of influences. It might pass through a layer where the temperature changes, affecting its evaporation rate. It might encounter wind shear, where the wind speed or direction changes with altitude, causing the drop to drift sideways. It might even collide with other drops on the way down, growing slightly larger. By the time it reaches you, it has travelled through a complex, ever-changing environment. Not every cloud makes rain, even if it looks thick. Some clouds just don't have the right conditions. Maybe the air isn't lifting strongly enough to keep the process going. Maybe the droplets never grow large enough. Maybe the cloud dissipates before precipitation can develop. Clouds are constantly forming and dissolving, and only some of them produce rain. That's why you can see a sky full of clouds on some days, and still not feel a single drop. There are fair weather cumulus clouds, for instance. Puffy white clouds that form on sunny afternoons. They look substantial, and they might contain millions of droplets, but they rarely produce rain. The updrafts inside them aren't strong enough or long-lasting enough to allow droplets to grow to raindrop size. The clouds might only last for half an hour before they evaporate away. They're part of the atmosphere's constant churning, visible signs of convection, but they don't lead to precipitation. Only when conditions are more vigorous, when there's more moisture, more instability, stronger lifting, do clouds develop into rain producers. Raindrops are not shaped like teardrops as they fall. This is one of those common misconceptions that shows up in drawings and cartoons. But it's not how raindrops actually look. Small raindrops are often close to spherical. Surface tension, the force that pulls water molecules together, tries to make the drop into a sphere, the shape with the smallest surface area for a given volume. For very small drops, this works well, and they fall through the air as little round beads. Surface tension is a fascinating property of water. It arises because water molecules are attracted to each other through hydrogen bonding. At the surface of a water drop, molecules are pulled inward by the molecules beneath them, creating a kind of skin that tries to minimize the surface area. This is why water forms droplets in the first place, rather than just spreading out into a shapeless blob. The surface tension is strong enough to hold small drops in a spherical shape, even as they're falling and encountering air resistance. Larger raindrops can flatten slightly on the bottom. As a raindrop falls, it's pushing through the air, and the air pushes back. Air resistance pushes on the falling drop's underside, and this pressure can deform the drop. Instead of a perfect sphere, a larger raindrop might look more like a small hamburger bun, rounded on top, flatter on the bottom. The faster it falls, and the bigger it is, the more pronounced this flattening becomes. Very large drops can break apart into smaller drops. If a raindrop gets too big, the forces acting on it, gravity pulling it down, air resistance pushing up and flattening it, can become strong enough to tear it apart. The drop becomes unstable, and it splits into 2 or more smaller drops. This breakup helps keep raindrops within a certain size range. You don't see raindrops the size of baseballs because they would break apart long before they reach the ground. Most raindrops that hit the ground are somewhere between 0.5 millimeter and about 5 millimeters across. Anything much bigger than that doesn't survive the fall intact. The breakup process is surprisingly complex. A large drop doesn't just split cleanly in half. Often it develops an indentation on the bottom as air pressure pushes up. The indentation grows deeper, eventually forming a bag-like shape with a rim of thicker water around the edge. The bag can burst, creating several smaller drops from the thin membrane, while the rim breaks up into a ring of slightly larger drops. High-speed photography has captured this process in detail, revealing just how intricate something as simple as a raindrop breaking apart can be. The speed a drop falls depends on its size. A tiny drizzle drop might fall at less than a meter per second, slow enough that it almost seems to float down. A large raindrop might fall at around 9 meters per second, which is faster, but still not terribly fast. It's much slower than, say, a ball thrown by a person. The drop reaches a terminal velocity, a speed where the upward force of air resistance exactly balances the downward force of gravity, and then it falls at that constant speed the rest of the way down. Terminal velocity increases with drop size because larger drops are heavier relative to their surface area. A small drop has a lot of surface area for its weight, so air resistance slows it down more. A large drop has less surface area relative to its weight, so it can fall faster before air resistance balances gravity. But even the fastest raindrops aren't moving all that quickly compared to other things falling from the sky. A raindrop at 9 meters per second is travelling about 32 kilometers per hour, about the speed of a leisurely bicycle ride. Wind can tilt a raindrop's path so rain looks slanted. On a calm day, rain falls more or less straight down, but when there's wind, the drops get pushed sideways as they fall, and you see rain coming at an angle. Strong winds can make rain seem almost horizontal. The drops are still falling downward due to gravity, but they're also being carried sideways by the moving air, and the combination of those two motions makes the slanted streaks you see during a storm. The angle of the rain tells you something about the wind speed. If the rain is falling straight down, there's little or no wind at the level where the drops are falling. If the rain is at a 45-degree angle, the horizontal wind speed is roughly the same as the terminal velocity of the drops. If the rain seems nearly horizontal, the wind is much stronger than the fall speed. Sailors and pilots pay attention to these cues, reading the rain to understand what the wind is doing at different altitudes. The pattern of rainfall can change minute by minute as cloud layers shift. Clouds are not static objects. They're constantly evolving, growing in some places, shrinking in others, moving with the wind, responding to changes in the atmosphere around them. As they shift, the rain they produce shifts too. You might feel a heavy burst of rain for a few minutes, then it lightens to a drizzle, then it stops, then it starts again. These changes reflect what's happening in the clouds above you. Changes in updrafts, changes in the supply of moisture, changes in temperature. Rain is a conversation between the sky and the surface, and it's always changing. Sometimes these changes are organised into patterns. A line of thunderstorms, for instance, might move through an area over the course of an hour, producing bursts of heavy rain separated by lulls. Each storm cell in the line has its own internal structure, its own updraft, its own downdraft, its own region of heavy precipitation, and as the line moves, you experience each cell in sequence. First the leading edge with gusty winds and the first heavy drops, then the core with the heaviest rain, then the trailing edge as the cell moves away and the rain lightens, then a gap, a period of light rain or no rain, before the next cell arrives and the pattern repeats. Drizzle is made of very small droplets. Drizzle is its own category of precipitation, different from rain. The droplets in drizzle are tiny, usually less than 0.5 millimeter in diameter. They fall slowly and they don't make much sound. Drizzle often has a soft, almost weightless quality. It can make everything damp without ever feeling like a real rain shower. It's the kind of precipitation that barely makes a splash when it hits the ground. Drizzle often falls from low-layered clouds. These clouds, called stratus clouds, are the flat grey blankets that sometimes cover the whole sky. They're not very tall, and they don't have strong vertical motion inside. They're stable and calm, and the precipitation they produce is equally calm. Drizzle from a stratus cloud can last for hours, just a steady, light mist that seems to hover in the air. Stratus clouds often form when a layer of moist air cools just enough to reach the dew point. This can happen overnight, when the ground cools by radiating heat to space, and the air near the surface cools in response. It can happen when warm, moist air moves over a cooler surface, like when air from over the ocean moves over cooler coastal land. The cooling is gentle and widespread, and the resulting cloud is gentle and widespread too. The droplets in a stratus cloud are small and don't grow very large because there isn't enough vertical motion to promote collision coalescence or ice processes. What falls is drizzle, not rain. Showers are rain that starts and stops more suddenly. A shower is different in character from steady rain. Showers tend to be briefer and more intense. They come on quickly, rain for a while, and then stop. The rain might be heavy during a shower, then nothing, then heavy again. Showers are less predictable in their timing and location. Showers often come from clouds with stronger vertical motion. These clouds, called cumulus or cumulonimbus clouds, have strong updrafts inside them. Warm air is rising quickly, carrying moisture upward, and the clouds can grow tall in a short amount of time. Inside these clouds, droplets grow rapidly through collision and coalescence, and ice processes can be very active in the upper levels. The result is bursts of rain that can be quite heavy, but which don't last as long as the steady rain from a large weather system. A cumulonimbus cloud, the towering cloud associated with thunderstorms, can produce very heavy showers. These clouds can extend from near the surface all the way up to the tropopause, the boundary between the troposphere and the stratosphere, which is typically around 10 or 12 kilometers high in the mid-latitudes. The updrafts inside a cumulonimbus can be extremely strong, sometimes exceeding 20 or 30 meters per second. These updrafts can suspend large raindrops and even hailstones, allowing them to grow to impressive sizes before they finally fall. When they do fall, the result is a deluge, a shower that can drop centimeters of rain in just a few minutes. Steady rain can last longer when large cloud systems pass through. Think of a cold front moving across a region, or a low-pressure system spinning slowly overhead. These systems are big. They can cover several states, or even a large portion of a continent. They contain vast layers of clouds, and as the system moves, the clouds move with it. Rain can fall for hours or even days as the system passes, because there's just so much cloud and so much moisture involved. This is the kind of rain that settles in and doesn't seem to want to leave. The clouds associated with these systems are often stratiform, layered clouds that extend horizontally for hundreds of kilometers. Within these layers, there's gentle, widespread lifting of air, enough to sustain condensation and precipitation over a large area. The rain from stratiform clouds is typically light to moderate rather than heavy, but it makes up for that by lasting so long. A winter storm system can bring steady rain for 24 hours or more, accumulating significant totals even though the rate at any given moment isn't extreme. Some rain is light enough to feel like a mist. This is rain that you notice more by the dampness it leaves than by the sound it makes. It might be hard to see individual drops, but after a few minutes outside, your clothes are wet. The drops are small, the rate is low, and the whole experience is gentle. It's the kind of rain that feels almost meditative, quiet, and soft. Some rain is heavy enough to sound like a steady curtain. At the other end of the spectrum, heavy rain can be loud. It drums on roofs, hisses on pavement, and makes it hard to see across the street. The drops are larger, they're falling faster, and there are more of them per second. This kind of rain can fill gutters and create puddles in minutes. It has weight and presence, a kind of insistence that light rain doesn't have. Heavy rain can produce rainfall rates of several centimeters per hour. In extreme cases, such as with tropical thunderstorms or organized lines of severe storms, rates can exceed 10 centimeters per hour for brief periods. This is an enormous amount of water falling from the sky in a short time. The ground can't absorb it fast enough, so it runs off, filling streams and rivers, sometimes causing flash flooding. Heavy rain is dramatic and sometimes dangerous, a reminder that the atmosphere can move vast amounts of water very quickly when conditions align. Rain can fall in narrow bands or wide sheets. The distribution of rain is rarely uniform. Sometimes a band of heavy rain is only a few kilometers wide, and if you're on one side of it, you get drenched, while just a few kilometers away it's barely raining at all. Other times, rain falls over a huge area with little variation. The structure of the clouds and the dynamics of the storm system determine how rain is organized in space. Rain bands are a common feature of many storm systems. In a hurricane, for instance, spiral rain bands wrap around the centre of the storm, each one producing heavy rain and gusty winds. Between the rain bands, conditions are much calmer. If a rain band passes over you, you experience a period of intense rain, and then it moves on, and you're in a relatively dry area until the next band arrives. Even in smaller systems, rain can organise into bands aligned with features like fronts or lines of convergence, where winds from different directions meet and force air upward. Rain can be local, affecting one neighbourhood and not another. On a summer afternoon, a small thunderstorm might develop over one part of a city and dump rain there while the rest of the city stays dry. You can sometimes see this from a distance, a column of rain falling from a single cloud, with clear skies all around it. It's a reminder that weather happens on many scales, from continent-wide patterns down to individual clouds a few kilometres across. The localised nature of some rain can be surprising and even frustrating. You might check the weather forecast and see that rain is expected, but the rain falls on the other side of town and you don't get any. Or the opposite, the forecast says it will stay dry, but a small cell develops right overhead and drenches you. Forecasting the exact location of these small-scale features is difficult because they depend on local variations in heating, moisture and wind that aren't always well represented in weather models. Rain intensity is often measured as rainfall rate over time. Meteorologists talk about how much rain falls in an hour or how many millimetres or inches accumulate in a day. A light rain might be just a millimetre or two per hour. A moderate rain might be 5 or 10 millimetres per hour. A heavy downpour could be 20 or 30 millimetres per hour or more. These numbers help quantify something that can otherwise be hard to describe. How much water is actually falling from the sky? Rain gauges are the instruments used to measure rainfall. The simplest rain gauge is just a cylinder with straight sides, open at the top. Rain falls in, and you measure the depth of water that collects. More sophisticated gauges can record rainfall automatically, logging the amount that falls in each hour or even each minute. Some gauges tip a small bucket each time a certain amount of rain has fallen, and the number of tips is counted electronically. Others weigh the collected rain continuously. All of these measurements help meteorologists track storms, verify forecasts, and build up long-term records of rainfall patterns. Rain can cool the air as it falls. One of the side effects of rain is cooling, and this happens through a process that's easy to overlook. Cooling happens because some droplets evaporate, which uses heat. Even as rain is falling, some of the drops are evaporating, especially if the air they're falling through is dry. Evaporation is a phase change from liquid to vapour, and phase changes involve latent heat, energy hidden in the change of state. When water evaporates, it absorbs heat from the surrounding air. That heat is used to break the bonds between water molecules and turn liquid into vapour. As a result, the air gets cooler. This evaporative cooling can be significant, especially in dry climates. When rain falls into dry air, a lot of the rain can evaporate before it even reaches the ground, and the air below the cloud cools dramatically. That cool air is denser than the warm air around it, so it sinks, creating a downdraft. This is one reason thunderstorms can produce strong gusts of wind. The rain cools. The cool air rushes downward, and when it hits the ground, it spreads out in all directions, creating gusty winds. These downdrafts are sometimes called downbursts if they're particularly strong. A downburst can produce winds as strong as a tornado, though they're spread over a wider area and don't have the rotating structure of a tornado. Downbursts are especially common in arid regions where the air is very dry and evaporative cooling is very efficient. A thunderstorm over a desert can produce a tremendous downdraft even if very little rain actually reaches the ground, just because so much evaporation is happening during the fall. Rain can make a warm day feel softer and calmer. There's a psychological component to this certainly, but there's also a physical one. The cooling from evaporation, the increase in humidity, the change in light as clouds block the sun, all of these things combine to make the air feel different. A hot, dry afternoon can be transformed into a cool, damp one in just a few minutes of rain. The relief that rain brings on a hot day is something many people find deeply satisfying. There's a freshness to the air, a sense of things being washed clean. Temperatures drop, sometimes by several degrees in just a few minutes. The oppressive heat lifts. The air feels easier to breathe. This is one reason rain is so often welcomed after a dry spell. It's not just about the water for plants and reservoirs, it's about the immediate comfort it brings. After rain, the ground can release smells that many people notice. This smell is one of the most recognizable and pleasant aspects of rain. It has a fresh, earthy quality, and it's especially strong after the first rain following a dry spell. The rain smell is often linked to oils from plants and compounds in soil. One compound in particular, called geosmin, is produced by certain soil bacteria and released into the air when rain disturbs the soil. Geosmin has a very distinctive odour, even in tiny concentrations, and it's a big part of that after-rain smell. Plants also release oils during dry periods, and when rain hits the ground, it can vaporize some of these oils and carry them into the air. The smell of rain has a name, petrichor. The term was coined by two Australian researchers in the 1960s, derived from Greek words meaning stone and the fluid that flows in the veins of the gods. It's a poetic name for a common experience, and it captures something of the almost magical quality that smell has for many people. Petrichor is released when rain hits dry soil, and it's at its strongest after a long dry period when oils and compounds have built up. The smell can be detected at very low concentrations. Humans are remarkably sensitive to geosmin, able to detect it at levels of just a few parts per trillion. Rain can also clean dust and pollen from the air temporarily. Raindrops falling through the air collide with particles, dust, pollen, soot and other aerosols, and carry them down to the ground. After rain, the air often looks clearer because those particles have been washed out. The effect is temporary because new particles are always being added to the air, but for a while, the atmosphere is a bit cleaner. This cleansing effect is particularly noticeable in cities, where there's a lot of particulate pollution from vehicles, industry and construction. After a good rain, visibility can improve dramatically. The sky looks brighter, the air feels fresher, and distant objects are easier to see. The rain has literally washed the pollution out of the air, carrying it down to the ground where it can be swept into storm drains or absorbed into the soil. The air can feel fresher after rain because temperatures and particles shift. There's a combination of factors at work. The air is cooler, it's more humid, it's cleaner, and there are new smells from the ground. All of these changes together create that fresh, clean feeling that people associate with the end of a rainstorm. Light rain can create a steady, soothing soundscape. Rain sounds are one of the reasons people find rain relaxing. There's something about the consistency of the sound, the way it fills the space with a soft, continuous noise, that many find calming. It's not loud enough to be jarring, but it's not silent either. It's a kind of white noise, a background sound that can mask other, more distracting noises and help the mind settle. The soothing quality of rain sounds has been studied by psychologists and acousticians. White noise and similar sounds can help with sleep and concentration because they provide a consistent auditory environment. Your brain doesn't have to keep alert for sudden noises or changes because the sound is steady and predictable. This allows other mental processes to relax. Rain sounds also tend to have a pleasant spectral quality. They're broadband, meaning they include a wide range of frequencies but without any harsh peaks or jarring elements. Rain sounds change depending on what it lands on. The surface makes a big difference. Rain on leaves sounds different from rain on metal, which sounds different from rain on water. Each surface has its own acoustic properties, how hard it is, how much it absorbs or reflects sound, whether it's smooth or textured. These properties shape the sound the rain makes when it hits. Leaves soften impacts and create a gentle patter. When rain falls on a tree or a bush, the leaves catch the drops and absorb some of the impact. The sound is soft, almost muffled, with a light tapping quality. It's organic and irregular because leaves are flexible and move with each drop. The overall effect is gentle and natural, a layered sound as drops hit leaf after leaf. A forest in the rain produces a complex layered soundscape. Raindrops hit leaves at different heights. Some fall on the canopy high above, others on understory shrubs, still others on ground-level plants. Each level contributes its own sound, and together they create a rich acoustic tapestry. There's movement too, branches swaying, leaves fluttering, and this adds variation to the sound. Walking through a forest during rain is a multisensory experience, the sound enveloping you from all directions. Roofs can create sharper taps and steady drumming. Rain on a roof is often louder and more distinct, especially if the roof is made of metal. Each drop makes a clear, sharp sound. and when many drops are falling, it becomes a drumming rhythm. Roofs are hard and reflective, so the sound bounces around and can be quite noticeable inside the building. It's one of the classic rain sounds, the one people often associate with being indoors during a storm. Tin roofs are particularly resonant. A metal roof amplifies the sound of rain, turning even a light shower into a noticeable drumming. In some parts of the world, this sound is such a familiar part of rainy season that it's deeply embedded in the cultural experience of weather. People remember the sound of rain on the roof from childhood, associate it with coziness and safety, find comfort in it. Pavement can create a crisp, wide hiss. Rain on a street or a sidewalk has a different character. The surface is hard, so there's some sharpness to the sound, but it's also distributed over a large flat area, so it blends into a kind of hiss. It's a broad, diffuse sound rather than a series of individual taps. You hear it when you're walking in the rain or standing near a wet road. The hiss of rain on pavement is punctuated by the sounds of cars passing through puddles, water splashing against curbs, drops hitting umbrellas and coats. In a city during rain, the soundscape is complex and layered. Rain on all sorts of surfaces, wind rustling leaves and whistling around buildings, distant thunder, the hum of traffic. It's a busy, active sound environment, very different from the quiet simplicity of rain on a forest or a field. Grass can absorb sound and make rain feel quieter. Grass and soil are softer than pavement or roofs, and they absorb more of the sound energy when rain hits them. The rain still makes noise, but it's quieter, more subtle. You might hear the rain more in the air around you than on the ground itself. Rain on water can create overlapping rings and soft splashes. When rain falls on a pond or a puddle, each drop makes a small splash and sends out ripples. The sound is a mixture of the impact and the subsequent splashing and rippling. It's a layered sound, with each drop adding to a complex, constantly changing pattern. There's something hypnotic about rain on water, both visually and acoustically. If you watch rain falling on a lake or a quiet pool, you see countless rings expanding outward, overlapping, interfering with each other in intricate patterns. Each drop creates its own small disturbance, and these disturbances interact, creating a continuously shifting pattern of waves and ripples. The visual and auditory experience together can be mesmerizing, a display of simple physics playing out in countless simultaneous events. The size of drops changes the sound. Bigger drops make deeper taps. A heavy rain with large drops sounds different from a light drizzle with tiny drops. The large drops have more mass and more energy when they hit, so they make a louder, lower-pitched sound. Small drops are quieter and higher-pitched. The size distribution of the drops shapes the overall sound of the rain. Wind changes the sound by changing the angle and speed of impacts. Wind doesn't just move the rain sideways, it also affects how hard the rain hits surfaces. When wind is strong, drops can hit at steeper angles and with more force, creating louder, sharper sounds. The wind can also create variation in the sound as gusts come and go, making the rain louder and quieter in waves. Distance changes the sound. Rain far away can be a soft whisper. When you hear rain in the distance, it's quieter and less distinct. The sound has travelled through the air and some of it has been absorbed or scattered. What you hear is a kind of gentle murmur, a hint of rain rather than the full sound. It can be very soothing, this distant rain sound, because it's so soft and non-intrusive. A steady rainfall can become a natural lullaby because it is repetitive and non-demanding. The sound doesn't change much. It doesn't startle you. It doesn't require your attention. It's just there, constant and calm, and that constancy can help the mind let go of other thoughts and drift. Rain sounds are often used for sleep and relaxation for this very reason. They're predictable, they're soft, and they're easy to stop actively listening to, which allows them to fade into the background of awareness. Sometimes rain evaporates before it reaches the ground. This is called virga. Virga is a phenomenon that's easy to see once you know what to look for. Virga is common when air near the ground is dry. Imagine rain falling from a cloud into a layer of very dry air. As the drops fall, they evaporate, turning back into vapor before they can reach the surface. You can sometimes see virga as wispy streaks below a cloud. The streaks are the rain, still visible as it falls but fading away as it evaporates. From a distance, it looks like the rain is disappearing into nothing. Virga is particularly common in arid and semi-arid regions, where the surface air is often very dry. You might see a storm cloud with clear signs of precipitation, a dark base, streaks extending downward, but feel no rain at ground level. All of the rain has evaporated in mid-air. For someone hoping for rain to water crops or fill reservoirs, virga can be frustrating. The moisture is there, falling from the sky, but it never reaches the ground where it's needed. Evaporation during virga can cool the air below a cloud. Just as with rain that reaches the ground, evaporating rain absorbs heat from the air. This cools the air in the layer where the evaporation is happening. Cooler air can sink, changing wind patterns near the ground. The sinking air can create downdrafts and gusty winds, even if no rain is actually reaching the surface. This is one way rain can affect the weather even when it doesn't fall all the way to the ground. Dry air can turn rain into a brief moment rather than a long event. In arid regions, virga is very common. Clouds can produce rain, and that rain can fall halfway to the ground or more, but the air is so dry that the rain never makes it. You see the clouds, you see the streaks of precipitation, but you feel nothing. It's a reminder that the atmosphere is layered, and conditions can be very different at different heights. This is one reason you can see rain in the distance and feel none where you are. Even if a cloud is overhead and rain is falling from it, if the air at your level is dry enough, the rain won't reach you. Or maybe the rain is falling a few kilometers away, and the wind isn't carrying it in your direction. Rainfall distribution is rarely perfectly even. Some places get rain, others don't, even when they're close together. The atmosphere is always layering and mixing, quietly shaping what reaches the ground. Air is constantly moving, rising, sinking, mixing horizontally and vertically. These motions create layers with different temperatures, humidities, and wind speeds. Rain has to pass through all of these layers on its way down, and each layer can change the rain in some way. The atmosphere is not a simple, uniform medium. It's a complex, dynamic fluid, and rain is shaped by that complexity. Rain usually begins with air lifting upward. This is the fundamental starting point for most precipitation. For rain to happen, you need moisture in the air, you need that air to cool, and cooling usually happens when air rises. As air rises, it expands because the pressure decreases with altitude. Expansion cools the air, and cooling brings the air closer to its dew point. When the air reaches the dew point, condensation begins, clouds form, and if the process continues, precipitation can develop. Air can lift when the ground warms it. This is called convection. On a sunny day, the ground absorbs sunlight and heats up. The air in contact with the ground warms up too. Warm air is less dense than cool air, so it starts to rise. As it rises, it cools, and if it's carrying enough moisture, it can reach the dew point and form clouds. This is how many afternoon thunderstorms develop, especially in warm, humid climates. The sun heats the ground, the air rises, clouds grow, and rain falls. Convective processes are particularly important in the tropics, where strong sunlight and abundant moisture create ideal conditions for afternoon storms. Almost every day, cumulus clouds begin to form in the late morning as the sun warms the surface. By early afternoon, some of these clouds have grown into towering cumulonimbus, producing heavy rain showers and thunderstorms. The pattern is so regular that people can almost set their watches by it. Clear mornings, building clouds at midday, storms in the afternoon, clearing in the evening. Air can lift when it's pushed up a mountain. This is called orographic lifting. When wind blows toward a mountain range, the air has to go up and over the mountains. As it rises, it cools, and cooling can lead to condensation and clouds. The upwind side of mountains often gets a lot of rain because of this effect, while the downwind side can be much drier. The air has lost much of its moisture on the way up, so by the time it descends on the other side, it's relatively dry. Orographic precipitation can produce very high rainfall totals. Some of the wettest places on Earth are on the windward slopes of mountains, where moist air is constantly being forced upward. Mount Waialeal in Hawaii, for instance, receives more than 10 meters of rain per year on average because it's in the path of the trade winds, which carry moist air from the ocean and force it up the mountain slopes. The downwind sides of islands and mountain ranges, by contrast, can be surprisingly dry. Even though they're just a few kilometers away from the wet slopes, air can lift where warm and cold air meet along fronts. A front is a boundary between air masses with different temperatures. When warm air and cold air meet, the warm air is forced to rise over the cold air, because warm air is lighter. This lifting can produce extensive cloud systems and precipitation. Cold fronts, where cold air is advancing and pushing under warm air, can produce lines of showers and thunderstorms. Warm fronts, where warm air is advancing and rising over retreating cold air, can produce broad areas of steady rain. Frontal systems are a major source of precipitation in the mid-latitudes, where warm tropical air and cold polar air frequently collide. The boundary between these air masses is the polar front, and it's along this front that many of the storms affecting North America, Europe, and Asia develop. As the front moves, it brings changing weather. First the approach of clouds, then rain, then clearing as the front passes and different air moves in. Lifting cools air, which encourages condensation. This is the key mechanism. Without lifting, air wouldn't cool enough to reach the dew point, and without reaching the dew point, condensation wouldn't happen. No condensation means no clouds, and no clouds means no rain. Lifting is the engine that drives the whole process. Clouds grow where condensation is happening repeatedly. Once condensation starts, a cloud begins to form, and if the conditions are right, the cloud keeps growing. More air keeps rising, more moisture keeps condensing, and the cloud expands. In some cases, clouds can grow very tall very quickly, especially in unstable atmospheres where rising air accelerates as it goes up. Instability in the atmosphere occurs when temperature decreases rapidly with height. In a stable atmosphere, rising air cools at a rate similar to the surrounding air, so there's no tendency for the air to keep rising. But in an unstable atmosphere, rising air stays warmer than its surroundings even as it cools, and this makes it buoyant. It continues to accelerate upward, driving vigorous convection and rapid cloud growth. This is the environment that produces the most intense thunderstorms. Larger cloud systems can organize rain over wide areas. When weather systems develop, they can create clouds that extend for hundreds of kilometers. These systems can produce rain over entire regions, and the rain can last for many hours or even days. The organization of the clouds is tied to the structure of the weather system, where air is rising, where it's sinking, where the moisture is concentrated. Small clouds can produce quick, gentle showers. On the other hand, a single cumulus cloud might only be a kilometer or two across, and it might only last for half an hour, but during that time it can produce a brief shower. The shower might be light, and it might only affect a small area, but it's still rain, produced by the same basic processes of lifting, cooling, condensation, and droplet growth. The same cloud can shift from drizzle to steadier rain as conditions change. Clouds are not static. Their internal structure is constantly evolving. Updrafts can strengthen or weaken. The supply of moisture can increase or decrease. The temperature profile can change. All of these changes affect the precipitation. A cloud that's producing drizzle might start producing heavier rain if the updrafts strengthen and droplets have more time to grow. Rain is often the visible end of invisible processes, lifting, cooling, condensing, and growing droplets. What you see when you look at rain is the final product. You don't see the air rising, you don't see the cooling, you don't see the condensation nuclei, and you don't see the collision coalescence or ice processes happening inside the cloud. But all of those invisible processes are what make rain possible. The rain you feel is the culmination of a long chain of atmospheric events. Rain moves fresh water from the sky back to land and ocean. This is one of the most important roles rain plays on Earth. The water cycle is constantly moving water between the surface and the atmosphere. Evaporation lifts water from the ocean and the land into the air. Condensation and precipitation bring it back down. Without rain, the water that evaporates would just accumulate in the atmosphere and the land would dry out. Rain is the return trip, the way water gets back to where it's needed. Rain helps refill rivers, lakes, and reservoirs. When rain falls on land, some of it soaks into the ground, some of it evaporates, and some of it flows over the surface and into streams and rivers. This surface runoff is what keeps rivers flowing, is what fills reservoirs behind dams, it's what maintains lake levels. Without rain, rivers would run dry, lakes would shrink, and reservoirs would empty. Rain is the source of fresh surface water. The Amazon River, the largest river in the world by volume, is fed almost entirely by rain falling on its vast drainage basin. Millions of square kilometers of rainforest receive abundant precipitation, and all of that water eventually flows into the river system. The river carries more than 15% of all the fresh water that flows into the world's oceans, a staggering amount that speaks to the immense rainfall over the Amazon basin. Rain supports plant growth by bringing water to soil. Plants need water to survive. They absorb it through their roots, and they use it for photosynthesis, for transporting nutrients, for maintaining cell structure. Rain delivers water to the soil where roots can access it. In places with regular rainfall, vegetation is lush and diverse. In places with little rain, vegetation is sparse and specially adapted to survive on very little water. The amount and pattern of rainfall shapes entire ecosystems. Rain carries minerals through ecosystems in gentle cycles. As rain falls through the air, it can pick up small amounts of dissolved gases and particles. When it hits the ground, it can dissolve minerals from rocks and soil. As the water moves through the landscape, soaking into the ground, flowing into streams, seeping into aquifers, it carries these dissolved substances with it. This is one way nutrients are distributed through ecosystems. It's a slow process, but it's been going on for so long that it's shaped the chemistry of soils, rivers and oceans. Rainfall patterns influence where forests, grasslands and deserts form. Climate is driven by many factors, but rainfall is one of the most important. A place that gets abundant rain year-round might have a rainforest. A place that gets moderate rain might have forests or grasslands, depending on temperature and seasonality. A place that gets very little rain becomes a desert. These are broad generalizations, but they hold true around the world. Rainfall is a defining feature of climate, and climate determines what kinds of ecosystems can exist. Rain releases heat in the atmosphere when vapor condenses into droplets. This is the other side of latent heat. When water evaporates, it absorbs heat from the surroundings, cooling them. When water condenses, it releases that heat back into the air, warming it. This release of latent heat is a huge source of energy in the atmosphere. It's one of the main engines of weather. Thunderstorms, hurricanes, and other storm systems are powered in large part by the heat, released when water vapor condenses. That released heat can help drive winds and circulation. The warming from condensation makes air more buoyant, which strengthens updrafts, which brings in more moist air from the surroundings, which leads to more condensation and more warming. This feedback can intensify storms and create powerful winds. On a larger scale, the release of latent heat in the tropics is one of the main drivers of global atmospheric circulation. It helps create the trade winds, the jet streams, and the large-scale patterns of rising and sinking air that shape weather around the world. Rain is one way the atmosphere redistributes energy. The sun heats the earth unevenly, more at the equator, less at the poles. The atmosphere and ocean work together to move heat from warm regions to cooler regions, evening out the temperature differences. Rain is part of this redistribution. Water evaporates in warm places, carrying energy up into the atmosphere as latent heat. The water vapor moves with the wind. When it condenses and rains out in a different location, that heat is released, warming that part of the atmosphere. Through this mechanism, rain helps transport energy across the planet. Even light rain is part of Earth's constant balancing act. The Earth system is always trying to reach equilibrium, balancing energy in and energy out, balancing moisture between surface and sky, balancing temperature between different regions. Rain, even a gentle drizzle, is part of this balancing process. It might seem small and local, but it's connected to the global system. The water you experience as rain has often travelled through many places before. The water molecule that lands on your hand might have evaporated from the Pacific Ocean weeks ago, been carried across continents by the wind, condensed into a cloud over your city, and now it's falling. But its journey doesn't end there. It will soak into the soil, or run into a river, or evaporate again in a few hours, and then the cycle continues. Water molecules are constantly being recycled through the Earth system, and rain is just one stage in their endless journey. Your breath contains water vapor. Every time you exhale, you're releasing a small amount of water vapor into the air. It's a tiny amount, but it's there. If you breathe onto a cold window, you can see it condense into a thin fog. This is the same process that happens in clouds, just on a much smaller scale. Your breath is part of the water cycle, even if it's a minuscule part. A warm shower can raise humidity in a room by adding vapor to the air. When you run hot water, some of it evaporates and mixes with the air in the bathroom. The humidity goes up. You can feel it. The air feels thicker, warmer, more moist. After you turn off the water, the humidity gradually drops as the vapor condenses on cold surfaces or mixes with drier air from the rest of the building. But for a while, you've created a little humid microclimate in your bathroom. Cooler air holds less water vapor than warmer air. This is a fundamental property of air and water vapor. Warm air can hold a lot of moisture before it becomes saturated. Cool air can't hold as much. If you take a parcel of warm, moist air and cool it down, eventually it will reach. The dew point and the vapor will start condensing. This is why condensation happens at night when temperatures drop, and it's why clouds form when air rises and cools. That's why condensation can form on cold windows. On a cold night, the window glass is much colder than the air inside the room. When warm, moist indoor air comes into contact with the cold glass, it cools down quickly. If it cools below the dew point, the water vapor condenses right onto the glass, forming a layer of tiny droplets. This is the same process that forms dew on grass or frost on a car windshield. Rain reminds us that the air is full of invisible moisture. You can't see water vapor, but it's always there, mixed in with the other gases in the atmosphere. Rain is proof of that invisible moisture. It's the vapor made visible, transformed from gas to liquid, falling to the ground. Every raindrop is a reminder that the atmosphere is not just nitrogen and oxygen, it's also water, constantly shifting between phases. The water cycle never stops, even while you sleep. Right now, somewhere on Earth, water is evaporating from the ocean. Somewhere else, clouds are forming. Somewhere else, rain is falling. The cycle runs continuously, day and night, summer and winter, year after year. It doesn't pause. It's one of the most constant, reliable processes on the planet, a rhythm that has been running for as long as Earth has had an atmosphere and oceans. Some of the water in rain once evaporated from oceans far away. The atmosphere is well mixed over time and distance. Water that evaporates in one place can be carried thousands of kilometers by the wind before it falls as rain somewhere else. The rain that falls on a landlocked region might have evaporated from the ocean weeks ago and been carried inland by weather systems. The journey of water through the atmosphere can be long and complex. Some of it once evaporated from plants through a process called transpiration. Plants take up water from the soil through their roots, and they release some of it through tiny pores in their leaves called stomata. This process is called transpiration, and it's a significant source of water vapor in the atmosphere, especially in forested regions. A large tree can transpire hundreds of liters of water in a single day. That water enters the atmosphere and can eventually become part of a cloud and fall as rain. Tonight, you can let thoughts fall like rain. Quiet, steady, and then gone. Rain is a good metaphor for letting go. Thoughts come, they fall, they touch the surface of your mind, and then they flow away. You don't have to hold on to them. You don't have to examine each one. You can just let them pass like raindrops falling through the air, each one separate, each one temporary, each one part of a larger pattern that you don't have to understand or control. And as you rest, Earth continues its oldest rhythm, water rising, gathering, and returning softly home. This rhythm has been running for billions of years. It was running before there were forests, before there were animals, before there were people. It will keep running long after we're gone. It's one of the most fundamental patterns of the planet. Water moving from surface to sky and back again in an endless loop, a quiet exchange that sustains everything. Rain falls. It has always fallen, it will always fall. It's simple and it's complex. It's ordinary and it's profound. It's something you can watch from a window or feel on your skin. It's something you can hear and smell and measure. And it's also something you can just let be. Just another part of the world, doing what it has always done, soft and steady, cycle after cycle, drop after drop, returning home. Just one more small fact, and then we drift. The next story is about to begin. Please relax and enjoy.